conference on advances in observations and modeling of solar magnetism and variability. So this is part of a series of events which IAA has initiated in this year, the 50th year of IAA. Currently in the country, we have a very thriving solar physics community, and we have a very active solar physics group in the institute here. The IAA still continues to be the largest solar physics group in the country. So the aim of this conference is to bring the national as well as the international community together to take stock of all the developments in the field, and especially on the fields which are relevant for the big projects which IAA has taken up, the National Large Solar Telescope project, as well as the upcoming Aditya mission. So with that, let's start this session. This session involves now address by the director of IAA, Professor Annapurni Subramaniam, following which we have remarks by Dr. John Leibacher from the National Solar Observatory and the University of Arizona in the USA, and Professor Siraj Hassan, former IAA director. Let me first welcome our director, Dr. Annapurni Subramaniam, to address the audience here. Thank you. Annapurni, you can go ahead.
Yeah, thank you. I just wanted to share the screen. Yeah, okay. Just give me a second. Can someone unshare the... Yeah, thank you. Yeah, so I welcome you all virtually to the Indian Institute of Astrophysics. And just to make you feel physically present in the campus, this is the picture of the green campus out here in Bangalore. And welcome to the inaugural session of this conference. I just want to take you through what is this institute and our history for a few minutes. So the institute has a rich history, and it was established in 1786 as an observatory in Chennai, and which started operational in Nungambakkam in 1792. And this is the picture of the observatory building out there. And it started observations of the sun and the solar system bodies, etc. And later it was felt that it should have a permanent setup. And 1899, the observatory moved to Kodaikanal, and the observations also started. It functioned in Kodaikanal for quite a long period before it became an autonomous institute under the name Indian Institute of Astrophysics in 1971. So this year, which is 2021, we are in the 50th year of the formation of the Indian Institute of Astrophysics. And there's a Golden Jubilee year, which we are celebrating with various conferences and events. And this conference is also under the banner of IAA 50. The headquarters of IAA moved to Bangalore in 1975. Incidentally, the institute is under the Ministry of Science and Technology, and it is supported by the Department of Science and Technology. And incidentally, Department of Science and Technology is also in its 50th year. So this comes under the Golden Jubilee celebrations of DST as well. So DST 50 as well as IAA 50. So it's really a wonderful moment, and wonderful to have a solar conference which is befitting to the history of this institute. Just to give you a feel of what all activities Institute does overall, Institute has several campuses spread across the breadth of the country, and many of them located in the Southern Peninsula. In Bangalore itself, we have two campuses, one right here where I am sitting, and many of the faculty, the auditorium is located, etc. But we also have a campus in rural, which is in a place called Hosukote, about 30 kilometers from here, and where we have a very uh, very good facilities, including the MGK Menon Space Sciences Lab, where the VLC on Aditya L1 is getting integrated, the upcoming segment polishing facility for the 30-meter telescope, as well as the remote observing facility for the telescope, which is located up in the northern part of India, that is the Himalayas. The other observatory we have is Gauribidanur, which is also located in Karnataka, close to Bangalore. The Kodaikanal facility is the oldest one, which is located in Tamil Nadu. Kavalur Observatory, which was set up in 1960s, is also in Tamil Nadu, but that is for dedicated to nighttime observations. Leh, Hanle, and Merak are all located in the Ladakh region. And the Hanle already has this 2-meter telescope. It's been operational for about 20 years. And Merak is the site which is identified for the National Large Solar Telescope, NLST, the upcoming one. And Leh is the base station for both. And apart from all these, we also have, I mean, these are the footprints on the ground, but we also have our presence in the space where the IAA led the integration, design, development, integration of UVIT in collaboration with other institutions. And the UVIT is one of the very prominent payloads, that's the yellow tubes on this mission, which is AstroSat, India's first space observatory, which has already completed 5 years of its operation. To give you a feel, the AstroSat flies over Bangalore once in every 90 minutes. And the payload operation center of UVIT is located in this campus in Bangalore. A few pictures of these field stations. This is the Hanle Observatory, where you can see the 2-meter telescope and the 70 centimeter telescope. And these are operated remotely from the Hosokote campus. This building, I haven't shown the MGK Menon lab in this campus, but it'll come later. But this just help to communicate and do the observations remotely from this building. In sharp contrast, you can see the Kavalur campus, which is quite green, whereas the Hanle is at an altitude of more than 4,000 meters above sea level. It's a high altitude desert. So it's kind of very, very dry and absolutely no greenery. But Kavalur is quite green. It's in the middle of a Javada Hills forest area. This is the 2.3 meter VBT telescope, and this is the 1.3 meter JC Bhattacharya telescope. This is established recently. This is the Gauribidanur Daipur array used to study the CMEs, and more will be talked about in this conference. This is also the Kodaikanal telescope, which also is very relevant to today's conference. And this is the AstroSat, which is launched, the picture taken before its launch, getting integrated in the ISRO campus in Bangalore. So moving, I mean, to just tell you the kind of science done by the researchers in this institute, there's a very broad spectrum of research carried out, starting from solar system, sun, the solar system bodies, stars, their motions, their chemical abundance, etc., star clusters, star formation, young stellar objects, many such objects within our galaxy, and the galactic halo, globular clusters, etc., and the nearby galaxies, and the high redshift universe, and as well as cosmology. So researchers cover all the broad spectrum areas of research. And a huge amount of effort also goes in development as well as maintenance of all these facilities and keeping them operational. We have a highly skilled engineering team to support all these activities. So heritage is the daytime and nighttime and space astronomy. Kodaikanal Observatory is only 120 years old, whatever you feel like. And Vainamappa Observatory is completed 50 years, and Gauribidanur Observatory is more than 40 years. HCT, we had a part of this IA50, we had a conference earlier in September, I think. Yeah, September 25th, it completed 20 years of operations of HCT, which is a big milestone considering the hurdles in keeping the telescope live and performing in a very high altitude and very harsh conditions. This Crest campus houses the MGK Menon Space Science Laboratory. It's already delivered VUVIT and is about to complete the integration and delivery of the VLC payload on L1. The major presence in space with the UVIT and its operation, that is a milestone and indicating that we do have a credible contribution in this area. We have several international and national collaborations in research and development. We also have a very successful flagship student program leading to trained resources in astronomy and astrophysics and related areas, including astronomical instrumentation. We also have library and unique and invaluable archives. We also should mention that we also have a group of theory scientists working on various aspects of theoretical aspects, starting from sun dynamics, black holes, and cosmology, etc. So it's a kind of a very well-rounded team out here. And Kodaikanal has already made an impact with the release of the 100 years of data, which is publicly available. The HCT also continues to be very productive, and the UVIT and the AstroSat as such. And these are some of the facilities we have added in the recent years. And just to ongoing impactful initiatives are the IA is one of the leading institutions for the India's participation in the 30-meter telescope. And this building shown here is the upcoming segment polishing facility set up in the Hoskote campus. And its operation will be beginning very soon with the polishing of mirrors for the 30-meter telescope. It's a state-of-art facility for large segmented mirror polishing. The major payload VLC on Aditya L1 is getting integrated in the MG Cayman Sciences Lab, Space Sciences Lab. This is one of the pictures from there. And we also have recently set up a thermovac and vibration facility for qualifying small payloads for space. And the NLST initiatives are taking place in the Merrick site, and these are some of the pictures. And we also have collaboration with the Mauna Kea Spectroscopic Explorer Canadian Initiative, UCA, University College of London, IAC and GTC for segmented mirror things and science, etc., and many more collaborations. We also have very enhanced and impactful outreach and science communication initiatives. So I'm wishing you all a very productive and successful conference, and this is very befitting, as you see, considering the heritage this institute has in solar physics. So this is under the DST 50 and IA 50. So I wish you all a very productive days and ahead. Thank you.
Thank you, Professor Annapurni Subramaniam. So let me welcome now Dr. John Liebacher to say a few words.
Can you hear me, Rajguru?
Yes, I can hear you, John.
Can you see me?
Yes.
Well, that's not as much fun. Namaste, namaskar. Good morning, Bangalore. Thank you, first of all, very much, Professor Subramaniam for your remarks. Best wishes to all of you there in the conference room in Bangalore, in balmy Bangalore, quite early in the morning. My apologies for getting you started so early, and particularly to the many participants around the world. On behalf of myself, as the international members of the SOC, it's a pleasure and an honor to add our welcome to all of the participants on this auspicious occasion of the Golden Jubilee of the IAA and the DST, the Department of Science and Technology. Congratulations on the first 50 years to the IAA and DST for all already accomplished, and our very, very best wishes for the exciting science and projects that are on your doorstep. We've already heard about them, and we'll hear more during the conference. We particularly send our thanks and congratulations to Rajguru and Ravindra for pulling this celebratory conference together in these very difficult times, and to all the members of the SOC and the LOC, particularly the IT folks there in Bangalore for handling all these connections and uploading all the electronic content. We're all a bit, or more than a bit, zoomed out at this point after a year of more or less confinement, and there's certainly many challenges to virtual conferences like this. But the has made possible many, many more international participants than I think would have been possible in, quote, normal times. And thus, the virtual meeting really contributes to one of the primary goals of the conference, from my perspective, which is to help identify and encourage the scientific collaborations of the sort that should dramatically enhance the science from the Aditya L1 mission and LSD, but more about them later. I can hear you saying now, sit down, John. We want to get to the science. After all, Alphonse Sterling is first up. You're on mute. I'm okay.
Thank you, John.
Yes.
Yeah, thank you very much. So let me welcome Professor Siraj Hassan. Say a few words.
Okay, thank you. Dear colleagues and friends, this is in fact a very challenging meeting with so many people spread out all over the world. But anyway, let me start off by saying I'm really happy to have been given this opportunity to participate in the inaugural session of this meeting, which, as you heard, marks the Golden Jubilee celebrations of IIA and also of the Department of Science and Technology. This is perhaps a good moment to reflect on the Institute's achievements and contributions over the years. Solar physics has a rather old tradition going back to the discovery of helium in the total solar eclipse of August 18th, 1868 from Masulipatam and Vunapurthi by astronomers of the Madras Observatory. An important landmark in the growth of solar physics was the setting up of the Kodaikanal Observatory in 1899. This has provided very valuable, uninterrupted observations for over a century. There have been many noteworthy contributions from Kodaikanal, of which the discovery in 1909 by John Evershed of radial motion coming from the umbra of a sunspot is perhaps the most well known. It is possibly the first astrophysical observation showing the interaction between plasma and magnetic field. And this could play an important role in our understanding of the physical properties of sunspots and the evolution of solar activity. In December 2008, the Institute organized a meeting with the title Magnetic Coupling Between the Interior and the Atmosphere of the Sun to commemorate the discovery of the Evershed effect. Now, I noticed that several persons who are attending this meeting were also here at that meeting in 2008. So it's really nice that they would be able to, we would have the opportunity to compare notes with how things have changed in the field since then. Despite numerous observational and theoretical advances over the year, we still do not fully understand this effect. In his Venubapu lecture during the Evershed conference, that is in 2008, Douglas Goff asked the question, what is a sunspot? A solar cycle later, we are still struggling with finding a comprehensive answer. The various mysteries of the sun continue to daunt solar physicists. The subtle interplay among the complex processes taking place in the sun's interior and the atmosphere involve the coupling between the magnetic field and plasma, and these pose numerous challenges. A key to understanding this is one of the frontline efforts of people working in the field. And this would help us to understand a range of processes such as sunspots, prominences, flares, coronal mass ejections, to name a few. As we've heard, in recent years, the Institute has taken several new initiatives: the ground-based 2-meter National Large Solar Telescope, the space-borne Aditya L1 mission are just a few. In addition, as I had mentioned earlier, we have these uninterrupted observations from Kodaikanal, and these have been digitized and are providing very valuable information about the sun. During the course of this meeting, we will hear we will have more detailed presentations about these projects. I'm really happy to see that the meeting has evoked an excellent response from within the national and international community. The COVID pandemic has posed several logistic problems, which have nevertheless been smoothly overcome. And I congratulate the organizers for putting together a truly remarkable scientific program, and also for getting top national and international experts to participate. And also, as I mentioned, to coordinate the difficulties in the time zones. This promises to be a truly superb meeting, and I greatly look forward with much excitement and anticipation to hearing about the latest developments in solar magnetism and variability. Thank you.
Okay. Thank you, Professor Hassan. Just quick, we have 10 more minutes. John, if you wanted to add a little more, we have time. I mean, I'm not sure if I kind of jumped over to Professor Hassan before you finished. John, you can unmute and speak if you have anything more to add.
I can always keep talking.
Please go ahead, John.
You know me. Let me think just a second. These points have been mentioned already, but let me recall a bit of the history. Again, let's see if we get the camera going. Recall the history of the IA going back to the world-renowned station Kodai Canal going into the 21st century. Kodai was really the heart and soul for the first more than a century, and Bapu managed to transform that into what has now become the greatest solar institute in India, in the world. As is so often the case, the sun leads astronomy and astrophysics and science in new paths and attracts new researchers to its following, and encourages international collaborations that advance our science, the sort that we're trying to do with this conference, with the upcoming missions. We've had relations between the National Solar Observatory, its first director, Bob Howard, and his colleague, Bill Livingston, enjoyed very close relations with the IA and Kodai, with colleagues Shivaraman Singh, Professor Hassan, Gokhale, Javaraya, Gupta, Hirmat, and of course, Rajaguru and others. Remarkable collaborations that have advanced our science and enriched our lives. While the renown of the IA and solar physics program has sprung from Kodai and associated theoretical investigations, let's not forget the new technologies that have been brought to bear in solar physics with the radio observatory at Gauriavandanur. I'm sorry, I always have a problem pronouncing the name. I do apologize. But in particular now, the upcoming Aditya mission and long sought for LSC. Let me also congratulate the IA for its role in spreading solar physics throughout India with, as examples, Bhatanagar and Venkat Krishnan going to Udaipur, Banerjee to Nainital, and others, of course. And as well as to encourage you in your growing efforts to share the fruits of our research and our investigations with the public at large. We're very much part of the 21st century to assume our responsibility of sharing the excitement and also the knowledge that we're uncovering. I think it's already been commented on, the very large turnout for this conference. I think there are 350 people registered in total. It reflects the international importance that the solar group continues to maintain and the respect that it commands across India and around the world. So, congratulations, IA, on your 50th birthday. Best wishes for the next 50 years. Congratulations for the large Indian and international participation in this conference. When you throw a party, who's going to show up, and a lot of people have shown up. And it's I think promises to be a very important for solar physics around the world forum to encourage collaborations between international and Indian scientists, particularly concerning the upcoming Aditya mission and NLC, both of which again we'll hear in the conference. Dhanyavad, shukriya.
Thank you, John. That's excellent. So thank you all in this session. So let me first give you a 5-minute update on the structure of the meeting and some more details. So the first day session. So unlike usual conferences, we have scheduled these sessions kind of factoring in the time zones of our speakers. Most of them are abroad. So the structure of the meeting is not the usual way of going from the solar interior, atmosphere, and corona and outside like that. So we have designed the program to kind of accommodate our invited speakers. And the first day session structured around the high resolution observations of all layers of the sun from the photosphere to corona. And there's an event today at 6:30. I mean, you can start joining at 6:15. There's a session in memory of Professor Kumar Chitre. As you all might know, he passed away about a few months ago. So there's a session, about 1 hour long session at 6:30 today evening. And the late evening session after that, following that, is for discussing about the new initiatives and facilities and projects, including the Udaipur Solar Observatory and the upcoming NLST project, the facility. And also we have people from Europe and the US covering the 1.5 meter Grigor Solar Telescope and the DKIST at Hawaii. So the second day and third day are mostly focused on coronal studies. This is in the context of Aditya L1 mission. And we also have sessions in the afternoon on Aditya L1. There are two sessions. People will cover the science and the instruments, which are going to be on Aditya L1. And the third day, again, we have a partly coronal science, followed by computational solar physics. And then we will move over to solar interior. There is a special event on the third day, the evening public lecture, Vainupappu Memorial Lecture by Professor K.R. Srinivasan, who is here among us in this audience now. He has joined now. He will be giving this Vainupappu Memorial Lecture titled The Dynamics of Convection in the Sun on Wednesday, 6:30 Indian time. So take note of that. And there's one more late evening session on that day. It's on solar interior. That's after 8:30 in the evening. And the last day will be the sessions on dynamos, cycles, and synoptic solar physics. And the last session will be on radiative transfer and models of solar atmosphere. And we have the conference summary again in the late evening on the last day. That will be by Professor Venkat Krishnan and Professor Arnav Rai Chaudhary, two well-known senior solar physicists in the country. So with that introduction, let me also update you that when you join in the meeting, please use your full name so that we identify the participants. And as I have all informed you in the email, the poster presentations will be on the website. If you look at our conference website, all of you have registered there. So if you log in there, you will find a link for viewing the posters. And most of the posters are in, and you will be able to find that in the website. And also we have set up a Slack channel. I have informed you all about it. And you please join in the Slack channel, where the poster presenters are also uploading their posters with audio files. And that gives a very nice environment to discuss and interact. And yeah, that's all. That's with that. let's take a 5 minutes break now. We will come back in 5 minutes for the first session of the meeting, first science session of the meeting. Okay, see you all in 5 minutes. So you can continue to stay there. We will start in 5 minutes the regular science session. I request the chairs of the sessions to please log in and take over. We'll start in 5 minutes, the science session. Thank you.
Hello, may I try to share the screen?
So should we warn you at 22 minutes or something? So
Yeah,
that
this sounds good.
Yeah.
Yes.
So Vaibhav, you can, I mean, I will also keep the time and you can, keep the time and conduct the session. About this question and for the 15-minute presentation, I think we'll warn at 12 minutes.
Okay, fine. Yeah.
So depending on this, how much time, I think it's already 8:45 in my clock.
Yeah.
So I don't know if Rajguru should give the green flag maybe.
Yeah, go ahead. Yeah.
Okay, thanks Rajguru. So
okay, I'll try and share now again.
Yeah, you can start sharing. So welcome everyone to the first scientific session of IIA 50 Solar Conference. So we have 3 talks in this session. And for the questions and answers, I would request you to raise your hand so the chair can see who is going to ask the questions, or you can also indicate in the chat box. And additionally, I will also keep posting the link for the Slack channel, and I request the speakers as well as the audience to go to the Slack channel where you can upload movies, your PDFs, ask questions, and the interaction would be much more fruitful because we would be time limited here. So with that, let us start the session, and Vaibhav, you can take over and introduce the speakers. And I will also keep the time and just warn the speakers, the 30-minute people after 22 minutes, the 30-minute talks.
Okay, thank you, Piali. Welcome everyone. And so the first talk of today's session will be given by Alfonso Sterling, who is from NASA MSFC. And he'll be talking on overview of solar fine structures, chromospheric spicules, and coronal jets. So Alfonso, please go ahead.
Okay, thank you very much. And I'm very happy to start this meeting. Okay, so yes, as you've heard, I'm at NASA Marshall Space Flight Center, and I was given the topic of high energy phenomena at small scales. And so I decided to limit this to 2 specific type of phenomena, spicules and coronal jets. And there are a couple of reasons for that. First of all, there's a vast myriad of small scale phenomena at high energy on the sun. And it's impossible to cover all of them. So I had to pick some. And also, there are so many experts in the audience that these are 2 areas where I can compete in giving some opinion and some ideas, since I've thought about these a little bit. So with that, let me go on. Both features, they are similar in that they are both jet-like geysers that shoot out from the sun. And of course, they're on quite different size scales. Now, spicules traditionally are chromospheric features. Actually, if you really want to get pedantic about it, they're chromospheric features seen at the limb of the sun, and they were first observed well over 100 years ago. And there are a number of very good studies and reviews of them. You can see some examples right here. So there is a long history of spicule observations, especially going back to when, with H-alpha and chromospheric observations, people would see flares or something, and then what else are you going to look at? Well, from the ground, then spicules are always there. So there were a lot of studies, but I'd say that there's been a revolution of spicule ideas and studies since about somewhere around 2000. And of course, it depends on how fine you want to get with it. But then we started getting some very good observations with instruments such as the TRACE satellite, I should have added, and Hinode really revolutionized the view. and iris, and also the ground-based has really stepped up. Anyhow, I should move on since time is moving on. Okay, I will get to chronojets in a bit. So first, a view. This is looking with Hinode solar optical telescope, and you can see the spicules protruding above the limb and shooting out. So this is calcium-2 observations. What I've just shown you is looking toward an active region at the limb. This is looking more toward a polar coronal hole. And so you also see very similar structures that are ghost-like, that are, well, sometimes moving out and sometimes twisting around. So these are the spicules, and these are in the chromosphere, and you can get an idea of the size by looking at the curve of the limb here. Well, what are some of their properties? There are various discussions, but again, I'd say for the size in general, there are a few arc minutes, 1 to, let's see, I'm sorry. The lifetime is about 1 to 10 minutes, and the size is like less than or about 10 arc seconds at the maximum, and their widths, an arc second and much finer also in detail. The density of them is like that of the upper chromosphere, despite the fact that they shoot well into the corona, where the density is about 3 orders of magnitude lower. To balance the energy of gravity requires about 10 to the 24 to 10 to the 25 ergs. And there may be more energy that is required to make them have their various motions. They congregate, when you look on disk, at the edges of supergranular networks. And that was the first hint that they must have a strong magnetic field connection. On disk, they're called various things. They're called mottles, RBEs, RREs, straws, enhanced spicular activities, to name a few, and sometimes they're just called spicules, even on the disk. Sometimes they show evidence of spinning motion, which might be a good hint to how they work. There's talk about spicule types, and I'll be quick with this. So this is what are called type 2s, the ones seen in the quiet sun and the coronal holes. So they tend to be faster and shorter lived than the other ones that are called type 1s. And they also tend to not show a return to the surface. They tend to go up and then fade. These are the type 1, which are seen mainly in the active region areas, and they tend to move up and down and live a little bit longer. Now, there has been a lot of talk about these types, and in fact, we go here to the bottom line. There's a question of whether type 1 and type 2 are really the same thing. And Shibata and company have the strong view that they're really the same thing, but just seen in different areas and working with the same mechanism. Depontu and colleagues have a very different opinion, thinking that they're very different objects. Personally, I must say, I don't mind at all the names type 1 and type 2 because they describe things that look different, that seem to have different properties. But that does not mean that I'm convinced that they necessarily are driven by different things. So I'm okay with the idea that we describe them and use different names to describe them, but then we still have to figure out what the mechanism is. And the mechanism may or may not be the same for the two types. Okay, this is a view on disk of spicules in H alpha. And you can see that it kind of outlines a supergranular network. And this is about 1 arcsecond resolution that we're looking at. And this is the way spicules were looked at for 100 years. But more recently, we've had better views. This is the same view. I've just degraded this very fine view from Samantha et al. Very high resolution from Big Bear of spicules. So this is telling us new things about them. Now the generation ideas, those are varied. I'm not going to discuss the older ideas. You can see Becker's for that. There are the wave ideas, and basically the wave ideas are pretty similar. They talk about, so you have a vertical flux tube in the atmosphere, and down at the base you just put a disturbance, and that causes an upward propagation of waves, of acoustic waves. Those acoustic waves can steepen into shocks, and then they push the chromospheric material up into the corona. Now, de Pontu et al. In 2004 and subsequently really showed very nicely that these spicules, at least the type they call type 1, can be correlated with the P mode waves. So it might be that the P modes are driving acoustic waves that shock and drive these spicules. Alphane wave ideas have also been around for a while, and there, instead of just a bump at the base, you give a twist to the bottom of the flux tube, and then that propagates up, and then in second order that can turn into a shock and raise the transition region. Let me think about my timing here. Yeah, I think I do want to move on. Okay, so there are other ideas that are coming around, especially I'll mention the ambipolar diffusion idea of Martinez, Sarkoza, and de Pontu et al. And this basically, they've done some very involved numerical simulations in Oslo and elsewhere. And by including a lot of physics, including ambipolar diffusion, they believe that they can explain what they call the type 2 spicules by magnetic fields that are in the photosphere and just above the photosphere that would be kinked, but because of the ambipolar diffusion, these flux tubes can snap up through the plasma, and this whipping motion can generate a spicule. All these are great ideas, and we aren't sure exactly what works yet, and this takes more study. Okay, let me go on. Okay, let me go on now to coronal jets. And I'm going to come back and make a connection to a possible connection to spicules. That was another idea too that we've been working on. Okay, but coronal jets. This is a very wonderful movie from Jonathan Certain et al. This is from Hinode XRT, and you can see in X-rays these long jets coming out and like this. Okay. So they have been observed since the Yoko days, at least very well since the Yoko days. And Yoko actually saw them mainly in active regions. So that's what it did. Hinode X-ray telescope found that they were also plentiful in polar coronal holes. And that's what I was just showing. And they're also, of course, visible in EUV and in other lines also. Just to give an idea of their properties, in polar coronal holes, Savcheva et al. Measured them to have lengths of about 50,000 kilometers on average, and widths of something like 8,000 kilometers. And I failed to mention for spicules. Spicules are really ubiquitous. They're really in the chromosphere all the time. They're all over. There are maybe 1 million of them on the sun at one time. Solar coronal jets, of course, are more sparse than that. There are about 60 of them per day in the polar coronal holes. So, you know, a few hundred on the sun per day. And that's how often they are. I will mention that we have observations showing that they spin, also are often will spin. So let's look at some of them. Okay. Right. So anyway, on the left here, we see an X-ray view. This is from XRT of a jet, and you can see that the spire is there, and there's also a bright point that shows up. And this bright point often occurs, and often it's lopsided. The spire is here, and then off to one side is this bright point. And this was seen back by Shibata and Shimojo and company back with in the Yoko days also. We looked at this with AIA when those observations became available. And what we found is that often when we get these jets like this is the same jet, and you can see that there's a dark mini filament is what we call this, that erupts out from one side of this jet. And that is just where this bright point occurs. And we have several other examples of that. Here's one more. You can see this spire here and X-rays again. And you can see a brightening over here off to the side. And if we look in the AIA, we see this filament here. It doesn't erupt fully, but it still gets up and it seems to make this, this hazy jet in EUV, and the bright point down here from where that filament erupted. Okay, one more example. There's a dark artifact here, but this is also showing a nice jet and a bright point right here. And if we look in the EUV, we see a nice mini filament erupting out here. So that seems to be a pretty general picture in a lot of jets anyway. And to us, it looks just like a large scale eruption. Now we're looking with the normal filament eruption, and you can see the filament erupting out, and of course there's a flare beneath it. So we think this is basically the same story occurring here with the jets. So this is the way we envision the magnetic structure. This is in a coronal hole the way we pictured it here. And basically it's all one polarity negative here, but then there's an intruding positive polarity. And if you take a cross section of that three-dimensional anemone region, you'll have two lobes like this. One side of it contains a mini filament, so it has shear here built up. This erupts outward, and it makes a flare just like a normal flare would with the reconnection beneath it. Either before or after this reconnection here, you also get reconnection here when this mini filament runs into this far side, oppositely directed open field. And this makes, of course, an open field here. And this is where the hot material leaks out and causes the jet. And also there's a cool material that can leak there. Okay, what causes the mini filament eruption? Well, we looked on disk, and others have too. And here's an example of an on disk mini filament erupting, making a jet. This is all AIA. On the left, it's 171, and you can see the mini filament very nicely erupting out. And you can see the bright point in the 94 on the right. If we put this with a magnetic field, we find that often there's mixed polarity, just like we had envisioned with that earlier study. And what happens very often, if we watch this magnetic field development over time, is like this. We often find that there's cancellation that goes on at the place where the mini filament erupts to make the jet. And so we found that we get this sort of picture where, okay, on the right-hand side, this is showing magnetic field elements coming together opposite polarity, and then the red line is showing where the jet formed. So cancellation occurs, and very often the jets occur just after that cancellation does. Okay, there have been some largish studies of jets and quiet regions and coronal holes. And let's see, basically the upshot here is that at least in our studies, we find that many filaments are present in virtually all of the jets. And flux cancellation occurs when we look on disk. And this McGlasson et al. Study found about 85%, at least they're consistent with many filament eruptions. Some other studies have found values that aren't as high as ours, but we might be looking at them differently. We don't know, we have to sort that out. Moulet et al. With 20 jets find that 50% are connected with flux cancellation. Kumar et al. Find that about 70% have many filament eruptions, and only about 22% they report with flux cancellation. They favor that the fields, instead of canceling, they actually cause, there's a shearing motion that leads to the eruption. So maybe that's going on in some cases. Okay, I'm not going to say anything about active region jets right now. They seem to look a little bit different from the quiet ones, but I think they're basically the same, but the magnetic field is more complex, so they look different. But now quickly, let's ask the question, do jets exist on smaller size scales? Now we have this plot here, and I've said that the jets, they often form from mini filament eruptions, and they have a mini flare with them. Well, we know that large flares come along with large regular filaments erupting. So let's say for fun that they really are the same thing, but on a different scale. So if you plot the number of events, the number of eruptions versus the size of the filament, then on the rightmost point with the lowest number, those are to represent the large scale filament eruptions and regular flares. So there are a low number of them, but the size of the filament is 30,000 to 100,000 kilometers, very big. The middle point is jets. So the numbers are, smaller. The filaments are only about 10,000 kilometers, and you get, some medium number of them. What if we extend that back down, the size scale down to the size scale of spicules? What would that tell us? Well, that's the left-hand point. And you see that there's a big error bar in the y coordinate. And that's because it's hard to know the exact number of spicules on the sun. But basically, we notice that it's plausible that at least some percentage of spicules really are small-scale jets. And depending on how that error bar is and how exactly the slope of this line is, it might explain a lot of spicules. We don't know, but this is an idea we wonder about. We have seen some spicule-like things, jet-like things on smaller scales than the normal jets. This was seen by Noralfi and Stemborg at the base of plumes, and they called these things jetlets. These are seen in EUV and in UV. And Panesar et al. Looked and found them to be not only at the bases of plumes, but also in the more general magnetic network. It's also similar to work done by Davina-Ennis and et al. And others too. So here you can just see, this is just a small scale jet that's going here with iris observations. And we can see similar hints of the things in AIA, but of course it's hardly resolved there. But the very important thing is we also believe we can see often canceling magnetic fields in these areas too at the base of these things. So they seem to be similar to the way the large scale jets are. Okay, so how about the idea that spicules might be small scale jets? Well, this is from a study that
3 minutes left.
Okay, this is from a study that we did some time before. Let's see. Well, it was a while ago, but before AIA, really, in 2010 or so. And you can see on the left, this is from Hinode ice, and we see an eruption of something that we know is now now would be a jet in AIA, and we saw that it was a jet in XRT. Well, I looked at this in the calcium on the right. This is calcium 2 from SOT. So the small things here, the small things in this thing on the right, those are real spicules seen in calcium. But you see that thing extending out there, that is this jet that we're seeing, but looking in the calcium. So that looks like, basically it looks like spicules too. So in this image here, the saturated ones are the real spicules, but the thin hazy ones, those are from the jet. So they look like spicules if you just look in the calcium. So anyway, let me say here that Samata et al. Found some similarities between real spicules. When they look at the base, they see that there's magnetic interactions and activity at their bases, and that might be similar to the activity, the magnetic activity we see at the base of jets, at least in some cases. And also, this is a close-up of one of the Samata et al. Events, and it looks like there's a real spinning motion here. And we know that a lot of jets spin. So there are some similarities. There are lots of outstanding questions. You can guess many of them. Let me just put here a summary. There's been a vast improvements in spicule observations in recent years. Similarly, new simulations are improving our understanding. And with the help of these new tools and future ones, we hope to be able to understand the mechanisms for sure of some of the spicule populations. For jets, I'd say we're approaching a good understanding of how they work. We have to work out some details and confirm some things, but at least for some of them, some percentage, we think that they're small filament eruptions. I think a lot of percentage, but anyway, at least some of them are that way. We need more simulations. Wiper et al. Have done some, but we need some with flux cancellation. And also we have to think about how the large eruptions and smaller eruptions might connect, and maybe the large ones make filaments, medium ones make jets, small ones might make some percentage of the spicules, and we don't know how many yet. Okay, that's it. Thank you.
Thank you, Alfonso, for providing a nice overview of spicules and coronal jets and providing a connection between them. Now, I think we should go for questions. So please raise your hands if you have any questions. So let me see. Yeah. So the first question is from Tanmay Samantha. Tanmay, please unmute yourself and go ahead and ask question.
Hi, Alfonso. Nice talk. I just wanted to ask you about this association of X-ray jet with spicule. So do we often see this when these X-ray jets are there? And if we look at the foot point, do you think we in calcium will see spicule-like structure?
I don't know. That's a very good question. And I know of two studies, the one that we did and also another study that looked in the same way. They saw Cameo et al. Or maybe Cameo wasn't the first author. But anyway, there's a Cameo et al. Study where they also saw a very similar thing. They saw an X-ray jet, and in the EUV, they saw definitely a jet-like thing. And then they looked in the calcium, and they definitely saw something that, what I showed you was really enhanced a lot. So I think if you don't enhance it and you just look at it normally, then it may look really like the regular spicules. We have to do more of that.
Okay. So next question is by Vishal Upendra. Vishal, go ahead and ask your question.
Thanks, Vaibhav. Can you hear me?
Yes.
Yeah. Thank you, Alphonse. That was a very nice talk. I have a basic or probably a general question. How are these jets different in coronal holes and Quetzalcoatl? I mean, do you see any differences in any properties?
Okay, I think between coronal holes and quiet sun, I think the properties are not very different. We've looked at them and they look very similar. I don't know about average heights and everything may differ a little, but they really look the same. There's many filament eruptions often seen, and cancellation at the base is often seen. But if you go to active regions, they kind of look like they have a different character. You don't as often see the mini filament itself, but we've done some studies where we think the magnetic structures are still the same. So I'm thinking that the filament may very rapidly, in active regions, very rapidly go onto the open field and become just large sheets of material as opposed to this closed flux that we can see in the quiet sun. So that's the boundary that I really would like to nail down, that they are the same. Incidentally, the fact that I think jets work the same in active regions and in coronal hole / quiet sun, even though they look quite different. That's what really gives me pause about spicules too. It might be the magnetic field properties of active regions and the dynamic of the magnetic field that makes the same mechanism operating in the quiet sun and coronal holes give something that looks quite different in the active region. I don't know, and Bart and his friends aren't on, I think, so they won't attack me too much, but we don't know. And, so there might be different spicules going on. But that's where I would draw the boundary. I think coronal holes and quiet sun jets are more or less the same.
Okay, thank you.
Okay, so next question is from Dipankar. Dipankar, please go ahead and ask a question.
Yeah, Alfonso, nice talk. So I was wondering, won't you think that where does the reconnection take place, in which atmospheric layers dictates whether you see the connection between the spicules and the X-ray counterpart? And also somewhat related to what the previous question was by Vishal, is the magnetic topology or the environment, which also dictates these signatures, whether you see at different heights in multiple wavelengths. So my point is, we understand probably it's all driven by reconnection, but where exactly the reconnection is happening in which layer, and the neighborhood or the topology of the environment is crucial to really connect this.
Yes. Okay. Good to hear from you. Thank you. Yeah, I think for jets that it's usually in the low corona, and I think it is in the low corona where the reconnection occurs. So that I think is, and I think that's where you get the X-ray jet. I've been talking with Ron Moore about this with the spicules, if it's going on there. He's a big pusher of this, actually. I should say quickly that Ron Moore has many decades thought that spicules work this way. And I when I was a grad student, I read this, and most ideas are quite different. And I thought that was nuts. I thought he was nuts. Even back then, I said, oh, he's nuts. But now he's shown me a lot of evidence, and we've done these joint projects. And now I'm thinking, well, I don't know, maybe I'm the nuts one, and he's right. But in spicules, it might be the chromosphere where the reconnection is occurring, and that might be one reason why the properties look different. And independent of whether all spicules are that way, but probably some of them work kind of the same way, even if it's a small percentage. But there, the reconnection might be going on in the chromosphere and give quite a different properties. Your point about the magnetic environment, I think, is really a crucial one vis-a-vis the jets looking different in active regions and in quiet sun / coronal holes. Yeah, go with that.
Okay, I think now we are overshooting time. So maybe we should move on to our next speaker. Thank you, Alfonso, very much for the talk. And those who are left, I would encourage them to ask questions in the chat box or in the Slack channel. And maybe, Alfonso, if you get the time, you can respond to them. Yeah.
Yes, but maybe in the morning after I get up, but I'll be here for a couple of hours.
Yeah, please log into the Slack channel. I'm sure there will be many more questions.
Yes.
You can log in anytime then.
Yeah. Okay, so moving on. Now, the next talk will be given by Bhuvan Joshi, who is from Udaipur Solar Observatory, PRL, on the signatures of 3D magnetic reconnection in circular ribbon flares. So, Bhuvan, please go ahead.
Yeah, good morning. So am I audible?
Yes.
So thank you, Vaibhav. And
Bhuvan, your presentation is not in full screen.
Yeah, sure. I'll do that.
Okay. Now it is fine.
Yeah, sure. So, so I'll be talking about this 3D magnetic reconnection in solar flares. So in particular, the circular ribbon flares, because they are thought to be strongly associated with the 3D magnetic reconnection. So I thank organizers for giving me this opportunity. And also I thank my collaborators. So basically I'll try to give an overview of the work done by our group in the last couple of years in this direction. So let me begin with the standard flare, and then let me tell you the difference between the standard flare ribbon and the circular flare ribbon. So this, the images here, they show what we call as standard flare ribbons. So these flare ribbons have been traditionally observed by H-alpha observations, as you can see in the top panel, and also in UV and EUV. So what we see is that when a flare progresses, we have the formation of large elongated brightenings, which we call as flare ribbons. And if you compare these brightenings with the magnetic polarities in the photosphere, then you will find that the one ribbon is on one kind of polarity, while the other ribbon is on the negative magnetic polarity, opposite magnetic polarity. So in this case, we have this western flare ribbon and eastern flare ribbon, and they are occurring on the negative and positive polarities respectively. So this is the standard typical flare ribbons. A very important properties of these flare ribbons is that they separate from each other as the time progresses, as you can see here. And their separation is perpendicular to the polarity inversion line. And this is a very important characteristic of the parallel ribbon, which has led to the standard flare model, which I'll discuss after a short interval. Another important property of a standard flare is the appearance of this loop top source, which you can see here by these white contours, and also in this animation by these blue contours. And these coronal sources can be nicely seen for those events which occur near the limb. For example, this is a very nice animation which shows how the coronal loops appear and then how they progress upward in the corona. So we have flare ribbons here as well. You can see there are two flare ribbons, and hard X-ray high energy sources are lying on these two flare ribbons. And in consort with the development of the flare ribbons, we see the development of this coronal sources. And later on, we see the formation of post-flare loops that connect the two flare ribbons. So this is the standard picture, and essentially the observations of the loop top source, parallel flare ribbons, and post-flare loops, they have confirmed this 2D magnetic reconnection scenario in solar flares. So in which we have a flux row, which can be observed as a prominence, or it can be observed as a CME in the source region, or a filament for the disk events. And when this flux row rises, it stretches the overlying loops, and therefore the reconnection begins underneath this erupting flux row. And then the electrons get accelerated, and those accelerated electrons, they finally interact with the lower, denser regions of the solar atmosphere, and this creates the H-alpha ribbons. And the physics of the whole scenario is shown in the panels below. So this is the pre-flare phase in this left panel. where we have a polarity inversion line, and then there are sheared arcades. So the initial rise of the sheared arcades occurs due to non-equilibrium, and then this can involve or evolve into a flux rope as well. And when the flux rope rises upward, the reconnection starts underneath it, and then we see the host of phenomena like loop toxos, parallel flare ribbons, and the later formation of flare loops in UV, first in UV, then in EUV, then in UV, and finally in H alpha, which we call as post flare loops. Now let us move on to the 3D magnetic reconnection. So in 3D, the topological structure essentially has a separating surface, which is shown here by this gray area, which we call as fan. And then we have two singular field lines, which are called spines, which you can see here. So it's a positive null in which the spine field lines are directed towards the fan. So what I'm going to emphasize in my talk is that the circular flare ribbons are essentially linked with the topological structure of a 3D null point. So the standard flare model, it explains several features like the formation of parallel ribbons, formation of post-flare loops, the formation of X-ray sources in the corona. But essentially, a flare occurs in 3D. There are 3D features like coronal sigmoid, twisted flux rope, J-shaped flare ribbons, and circular flare ribbons. And we need this 3D reconnection to explain such features. So there are many papers, excellent papers in the literature that discusses the standard 3D reconnection. So in fact, a two-ribbon flare can happen in 3D models without any eruptions. And we need to take into account of the quasi-separating layers for that. And then you do see the movement of brightness. The whole flare ribbon doesn't comes up at once. It builds up gradually, which is a kind of slipping reconnection or slip running reconnection, and depending upon the apparent slippage speed of the reconnecting field lines. So here is an animation from our work. So you see, as the flare progresses, we see a perfect circular ribbon formation. You can see here, I'll put my laser pointer here. And this is very, very interesting because it is, it is a different situation than the formation of parallel ribbons. Of course, later on, we do see complex structures like formation of parallel ribbon within the fan structure. And also another important thing is that if you take a larger field of view, then you will find that in consort with the development of this circular flare ribbon, we do see a remote brightening here. And this remote brightening essentially forms a remote ribbon. So now let us see what are the regions where these kind of flares take place. So the regions are called Animan active regions. So this is a typical Animan active region where there is an emergence of parasitic polarity. In this case, it is positive polarity in an opposite sign polarity of a larger dipolar region. And then you have an opposite polarity in the nearby region where the loops coming out from the fan can terminate. So the whole scenario can be seen if you do an extrapolation. This is a nonlinear force-free extrapolation in the region. You can clearly see the remote location here, a fan structure here, a null point, and below this fan structure, we have the inner fan lines, which we show by this yellow field lines. So this tells how the whole flare evolves. We have the formation of parallel ribbon within the circular ribbon. It's a complex case. Of course, this parallel ribbon forms much later, about 30 minutes later. So this shows that something else is going on here within the parallel ribbon area. On the other hand, the circular ribbon and remote brightening are simultaneous, which tells that there is ongoing null point reconnection, and later we have a kind of a standard 2D reconnection. So these are very much evident from these light curves of the parallel ribbon area, circular ribbon area, and remote brightening area. Of course, here we do see twin eruptions. The eruption 1 is here. The eruption 2 is from within the fan structure. The eruption 1 is essentially the reconnection at QSL halo surrounding the null point, while the eruption 2 signifies
3 minutes left.
the flux of eruption by the breakout type process. So the very interesting thing here is that if you do an analysis of magnetic decay index, and also if we draw the quasi-separated layers, which we show by blue isosurfaces here, then we find that within the fan dome, the region with magnetic decay index greater than 1.5 borders the null point QSL. Okay, so this tells, I mean, there can be chances of torus instability within the fan structure that can explain the formation of parallel ribbons. So I'll not go into the details, so I invite you to read our very recent article, which has appeared this month or last month in MNRAS, where we discuss this complex event. Now the question is, what causes the remote brightening, and what causes the coronal jets that we often see in relation with the circular ribbon flares? So there is definitely a time delay in the formation of circular ribbon and the remote ribbon, and many times these activities are associated with jet. Jet is again a 3D topological structure which provides evidence for the interchange reconnection. So in our analysis, what we found is that the remote brightening is because of the interaction of non-thermal particles at the remote ribbon. So this is, a usual picture. In some cases, people have seen that the remote brightening happens because of the dissipation of kinetic energy of plasma flow, but we couldn't find evidence for that. And the high QSL at remote location also explains this slipping reconnection scenario. So, so the details are given in our recent works. This is a very interesting picture in which we see quasi-circular ribbons successively. Okay, so there are 4 flares, F1, F2, F3, and F4, and they occur in a fan spine-like topology involving hyperbolic flux tube configuration. So you can see that there is a development of this anemone structure, but this anemone structure is very much different from the classical picture. It is extended in a lateral direction, and after each flare, there is a significant decay in this anemone active region because of the flux cancellation. And as we see that the flux cancellation is very important phenomena, the earlier talk also Alphonse discussed about it. All the events, they present circular morphology, but the circularity decreases. So that the first flare is perfectly circular, then we have quasi-circular flare, then we have arc-shaped structure. So we found that the photospheric field region also decays as the 4th flare proceeds. And this is also evident by the flux plot, where we see a lot of cancellation of the negative flux. So now I'm coming to the final works of this analysis, and of course of my talk as well. So here what we see is that the extrapolation suggests that this fan structure is quite extended, and also there are no null points in this fan structure. Okay, so this is not classical spine fan configuration. It is a kind of spine fan-like configuration where the fan structure is laterally extended, and also the open field lines are coming from the outer regions, and they are also spatially extended. So what we can say here is that it's a kind of pseudo-steamer configuration, and the absence of null points suggests that the situation is similar to the hyperbolic flux tubes. We have also plotted the region of high Q, and in those places, we do see the formation of flare ribbons due to the reconnection at QSL, and there are also evidences for the flux rope structure, which later on activates, and finally we see their eruption, which also causes a coronal mass ejection. So there are many complex things happening in this area. So the photospheric structure is longitudinally stressed, And the topology is similar to the topology of pseudo streamers, where we have a complex coronal configuration in which open field lines originate from positive polarity region enclosed and extended fan-like structure. So the cut-paste type reconnection occurs when the Q values reaches infinity, while the slipping or slip-running reconnection occurs when we have finite values of Q. Of course, the magnetic connectivity, the gradient is very high. So now let me invite you to read our recent work, which is a very new.
Bhuvan, sorry to interrupt, but may I request you to quickly wind up because.
Sure. This is my summary slide. Yeah, okay. So we have investigated different aspects of 3D magnetic reconnection, the properties of 3D magnetic reconnection and plasma response to it. And there are many complex cases in this circular ribbon flares. We do see the formation of flux rope within fan dome. We also find the formation of parallel ribbons. The parallel ribbons are formed because of the activation of the flux rope, which enhances the rate of null point reconnection by a kind of external forcing. There are cases where circular flare ribbons are associated with eject activity. And also I discussed one of the complex case in which the situation was like a pseudo streamer. So there is a reconnection at QSL which involve hyperbolic flux tubes. So a lot more studies are required to understand the 3D reconnection in such events. So with this, I'll stop here. So thank you very much.
Thank you, Bhuvan, for the nice talk. So since we are, the time is almost over, but I can take quickly one or two questions. Yeah, let me see. So please raise your hands if you have any questions for Bhuvan. Okay, seems like there are no questions. So I think we should go, we should move ahead. Thank you, Bhuvan, again for the talk. And so the next talk will be given by Koyoko Watanabe, who is from National Defense Academy of Japan. And she will talk about the source region dynamics of white light flares. So Koyoko, please go ahead.
Yeah, thank you. And pointer. Yes, thank you very much. I'm Kyoko Watanabe from National Defense Academy of Japan. At the first, I really appreciate to organizers to give me this opportunity. And in this talk, I'd like to discuss the dynamics of the white light flares from the analysis of observational data, especially observed by the Hinode satellite in Japanese solar satellite. First of all, let me introduce about the white light flares. And in association with strong solar flares, we sometimes observe the enhancement of visible continuum radiation, which is known as a white light flare. As you know, the most famous and the first white light flare was a Carrington flare, which was observed more than 160 years ago. The white light emission can be observed by the ground telescopes. However, white light flare is still rarely observed even in recent years. And that is because white light flare mainly associated with X-class flares. There have been cases of observations with smaller scale like C-class flare by satellites. This observation is observed by the trace. But the occurrence mechanism of white light flare is still unknown. As most white light events show close correlations in time and location with head X-rays and or radio emission. So there is some consensus that the white light emission originates from accelerated particles, especially non-thermal electrons. The structures of head X-rays and the white light emission are very similar as shown here. And so it seems that this emission mechanism also are physically linked. that by comparing the total energy of white light and hard X-ray emissions, the energy range of accelerated electrons that can produce the white light emissions are estimated as shown here, and these are the few tens of keVs. However, it is still unknown what mechanism and dynamics cause a white light enhancement. Especially, there is a problem concerning the height of white light and these hard X-ray emissions. Theoretically, white light to be emitted near the photosphere, but non-thermal electrons with energies around 50 to 100 keV are almost completely thermalized by the time they reach the lower chromosphere. And X-rays, hard X-rays are also emitted around the lower chromosphere at this height. So to reach down to the photosphere, the accelerated electrons would need to have energies greater than 900 keV. Now, even if such high energy electrons exist, there are not enough of them to explain the total energy of white light emission. Observationally, the relationship between the emission height of white light and hard X-ray has been measured from limb flares like this flare. Among these events, some shows white light emission at the photosphere, whereas in others it occurs in the chromosphere also. So independent of white light emission height, the position difference between white light and hard X-ray emission has been observed in some events. Conversely, other analytical methods show good height correlations as shown here. So determining the height of white light emission is not straightforward and remain an unresolved question. So here I want to show you one of the white light flare that were occurred at the limbs. So this is a limb flare, and discuss the emission height of white light. This is a X1.7 class flare. It occurred on January 27th, 2012. In this event, two rebounds of calcium emissions were observed as shown here, and the continuum emission from the white light flare was also observed by Solar Optical Telescope, SOT, on board the Hinode satellite. So this is almost the same location as where strong calcium emissions were observed along here. So maybe learning difference images, the emission is clear, white light emission clearly seen around here, especially in the red images. So you can see that this is the white light emission. So next we focus on that region, and this is a calcium image taken in the peak of the white light emission with continuum emission of each color contrast overlaid. So we focused on this region and found that the emission site of the red, green, and blue emission are slightly shifted with respect to the location of the calcium emission. And such location difference were not observed in the disk flare. And such location difference were not because this event occurred very near the limb here. Limb is located here. So there is a possibility that the emission location difference is due to the emission height difference. So next we put the slits, white slits shown here, and looked at the relevant emission location of white light and the calcium emission. So the calcium emission was seen around this position, and the peak of the red, green, and blue continuum emission were seen different position. As I said before, if this emission location difference is due to the emission height difference, the red emission is located more than 300 kilometers higher than the blue emission, and the 300 kilometers lower than the peak of calcium emission. The calcium emission exists from the chromosphere to the photosphere. And so the edge of the calcium emission, so that is also the same height of the peak emission of the blue band. That might be a photosphere, solar photosphere. So from this data, we can say that the white light emission was emitted from the photosphere. So next, we can calculate, we also calculate the temperature of the white light emission by fitting the 3-color data with a Planck formula, assuming the black body. So this is a temperature distribution of white light emission. And this is a solar limb. And so the temperature drop at the limb is due to the limb darkening. Continuum emission were located around here. They are located in high temperature region. The average temperature of the white light emission region is about 5,000 Kelvin. This temperature is affected, also affected by the limb darkening effect. And so the real temperature of the white light emission on the disk is about 6,000 Kelvin. When we check the temperature for each color region, emission region, this image, the average temperature of each emission region was calculated to be this table. The temperature of the green emission region was higher than that of red emission region. This time, the temperature of the blue region was lower than the green emission region. However, in the next image obtained 20 seconds later, the temperature of the blue emission region became higher than the green emission region. So if this difference of emission region reflects the difference of emission height, then each height was a different temperature. This result means that the lower layer reaches the higher temperature. So it implies that something, maybe the accelerated particles, that penetrates to the lower layer, the photosphere, and heat a lower atmosphere more than the higher atmosphere. So we don't know what this is, but there is a possibility that it is accelerated electrons and they reach the photosphere. And so next, I want to show you one of the other white light events that were discussed about the possibility of accelerated electron reach the photosphere. So on October 23rd, 2012, an X 1.8 class flare occurred, and the white light enhancement were also observed by Hinode SOT continuum bands. White light emission can be clearly seen around here. So in this event, white light emission, so this emission can be seen in almost the same location as the calcium ribbons, same as the previous event. When we take the difference images, we can easily find a large amount of white light emission. Now, RESI also observed this event and showed the high energy emission in the 800 to 7,000 KeV range. Using this data, we can perform the detailed analysis to search for any relationship between the white light and hard X-ray emission with high resolution. Also, we wanted to compare the white light emission with RESI hard X-ray images. These two ribbons were separated by less than 5 arc seconds. Axis. And so to compare with RESI data, we only use RESI RESI detectors number 1 to 4, which have good resolution. And so this is a calcium image at the flare peak time and with red, green, and blue continuum enhancements overlaid. The color contours the time variation of the hard X-ray emission from 35 to 100 keV. So in this figure, the most of the white lights corners are numbered here, and so they are related hard X-ray emissions. So in this event, Hinode EIS ICE, that EUV imaging spectrometer, also observed this flaring region from the flare start time. So this is an island 12 intensity, and so this is a Doppler velocity measured by the island 12 line. So this square, blue square, is the same image size as this SOT image. So some red shift was seen in some corners numbered maybe 3 and 4, and the strong blue shift was seen along the corner number 5 here. So this strong blue shift might be some ejection, but maybe including chromospheric evaporation along the corner number 5. So this SOT image and the white light emission was observed 3:15:40. And so these red and blue shifts were seen about 1 minute before the white light emission. So this means that some injection was maybe due to the particle acceleration, and the chromospheric evaporation and ejection already started at the start time before the white light emission. And next, we also checked the line profile for other lines. That is the island 14. They are along the blue shift and red shift region, and the area between them along here. So this table shows the electron density variation for 3 kernel positions. One is number 5, the blue shift region, and the one is K3 and 4, it's red shift region, and between them. But before the flare occurrence, the electron densities were 10 to the 9.8 per cubic centimeter. And then the density increased at all positions after the occurrence of the flare. Then at the strongly blue shifted region, it's K5 region, because most of the material were already ejected away from K5 region, so density decreased. On the other hand, in the red shifted region and the region in between, the density increased up to the 10 to the 12 per cubic centimeter. So most of accelerated electrons which have hard X-ray energies were stopped in a region with density of 10 to the 12 per cubic centimeter. So at the peak of the flare, the accelerated electrons, if they exist, couldn't reach the photosphere. On the other hand, at the start time of the flare, because the electron density was still not so high, so there is a possibility that the accelerated particles could enter the photosphere. So we have given about 2 examples in which it is so that the white light emission was generated due to the accelerated electrons reach near the photosphere. So next, I'd like to show a study that investigated the statistical aspects of white light flare. In particular, we investigated the relationship of white light and hard X-ray emissions. Here's an example flare events which occurred in the same active region, number 12192, and were observed Hinode continuum bands. So one is M-class flare, which have clear white light enhancements, and maybe see around here. And the other one is X-class flare, but we couldn't find any white light enhancements in Hinode images. And in this this event, hard X-ray emission were also observed in both events higher than 50 keV, but X-class flare didn't have any white light enhancement. For finding which parameter affected to the generation of white light enhancement, we performed the statistical analysis of white light flare observed by Hinode SOT continuum bands. And these are some results of our statistical study. We analyzed about 100 events, and half of them were white light events, white light flares, and the other half of them were non-white light flares. So we couldn't find any enhancement of visible continuum for these events. And we found that a white light flare has a shorter duration. This is a duration, and a shorter ribbon distance. There is a little scattered, but a white light flare located lower as a shorter, and a longer, stronger hard X-ray emissions shown here. And so this is a summary of statistical study. We obtained these results and obtained this schematic view of the flare. Usually, the white light flare have short emission duration, and have smaller loop and a compact source. So maybe the source area, this means the acceleration sites for the white light flare may be in near from the chromosphere. Now, on the other hand, the non-white light events have long duration and have the longer loop and the diffuse source. From these results, we obtained that a large amount of accelerated non-thermal electrons participate into a compact region within a short duration is a key factor of generating the white light generation. When we focused on the magnetic field at the acceleration site, so these results showed some feature that the white light flare have stronger magnetic field near the chromosphere. So this result is mainly came from the analysis of Nobeyama radio polarimeter data. So previously, we checked the microwave spectra observed by Nobeyama radio polarimeter from 2011 to the 2013, and compared with the existence of white light enhancement observed by the Hinode SOT. We only have 8 events at the time, which are simultaneously observed SOT and Nobeyama, and half of them were white light flare, as shown in blue lines. Now, when we check the turnover frequency of microwave spectra and normalized at 17 gigahertz, so all of the non-white light flare have the lower turnover frequencies. On the other hand, white light flare have the higher turnover frequencies. So microwave turnover frequency is obtained from this equation. And if we assume that the electron density doesn't change among these events, these results suggested the existence of a strong magnetic field. However, we only have 8 events for this study at the time. So this is not enough number of statistical analysis. So we performed similar analysis for longer period of data until 2017. Now we checked the turnover frequency from microwave spectra observed with Nobeyama radio polarimeter during the 2011 to the 2017. At the first step, we focused on the rooftop source near the acceleration site. So we checked the location of 17 gigahertz microwave emissions observed by Nobeyama radio heliograph, as shown in red contour in this figure, and the location of a RESI head X-ray emission shown in a green contour. That's in the SDO AIA imaging. As a result, we found 29 rooftop microwave events, Among them, 6 events are coming from the white light flares. 5 events are weak white light flare. This is also the white light flares. And 18 events, so most of the events are coming from the non-white light flares events. And for these 29 events, we fitted the microwave spectra, as shown here, at the peak time of 17 gigahertz light curve, and obtained the turnover frequencies. Then we checked the correlation with the soft X-ray class and found that most of the events have smaller turnover frequency, less than 17 gigahertz. And there is no correlation between them. So we couldn't find any evidence of strong magnetic field existence at the rooftop for white light flare events from microwave spectra. And then, so of course, we wanted to know the coronal field strengths along the acceleration sites, but there are no observations. And so next, we checked the photospheric field strengths along the white light emission region by using SDO HMI.
3 minutes left.
Thank you. And compared with the white light emission strengths of SDO HMI continuum. And we performed statistical analysis for 35 Hinode white light events. And we found that the field strengths of white light emission region for white light flare were roughly correlated with the maximum counts of white light emission. So if we assume that photospheric field strength is correlated with the field strengths at the flare acceleration site, so these results supported the existence of stronger field strengths for white light flares. And also, this analysis is not correlated with field strengths directly. We also calculated temperature distribution of white light emission, which were observed by Hinode SO2 continuum bands for 35 events, the same as previous. And we obtained the maximum temperature of the white light emission region and compared with the maximum counts of white light emission. Then we found that the intensity of white light emission is correlated with the force power of temperature. So this result means the Stefan Boltzmann's law holds. Okay, so this is a summary of my talk. So the mechanism of dynamics of white light flares are not yet well understood. However, some aspects were obtained from observational data. And it seems that the white light emission is located at the photosphere, and the lower layer is heated by the accelerated electrons. The density of the chromosphere on the white light emission region is thin enough for the accelerated electrons to penetrate. So there is a possibility that the high energy accelerated electrons directly reach the photosphere at the flare start time. And from the statistical studies, we obtained that a large amount of accelerated non-thermal electrons participated into the compact region within a short duration is a key factor of white light generation. About the magnetic field, we couldn't find any difference in the turnover frequencies with or without white light enhancement. However, it was found that the photospheric magnetic field of white light flare is strong. So if we assume that the photospheric field strength is correlated with the field strength at the flare acceleration site, so these results are supported the existence of strong field strength for white light flares. So that's all. Thank you for your attention.
Thank you, Kyoko, for the interesting talk. So now it's time for questions. Let me see who has raised a hand. Yes, Alfonso, please go ahead and ask your question.
Very nice summary of your work, Watanabe-san. Thank you. For your first event, you had temperatures all around 5,000 K, but they only differed by about 25 degrees in the 3 layers. Can you really measure it that accurately?
Yes, and so this temperature, this one. So we also measure the error of the temperature of this analysis, and the error of the temperature is roughly at 10 Kelvin or something.
Okay, thank you. One more question. For white light flares, is there a connection with CMEs? Because a short duration implies they might be compact and non-eruptive.
Yes. So I also think the white light emission is not correlated with the prediction of the CMEs. So I think CME prediction of the CMEs is correlated with clear duration.
Yes.
Yeah.
Yes. So of those 50 or 49 that had white light flares, how many of those had CMEs? Did you check that?
Yes, I also performed that study, but I forgot the results. But so I couldn't find a clear evidence of the clear correlation of the white light emission and the CMEs.
Thank you.
Yeah.
Okay, thank you.
Hello?
Oh,
Really?
Hello.
it's going.
Yeah, I think the next question is
Yeah,
by
next.
Rakesh. Yeah,
By Rakesh, yeah. Yeah, someone in the...
Maybe.
Hello? Hello?
Is it? Yes, hello?
Can I ask? This is Vinod Krishan.
Yeah, okay, Vinod will come to you after Rakesh. We'll just come to you. Okay.
Thank you.
Yeah, so nice talk. So my question is like, is there could be this white light flare and non-white light flare just due to some lack of temporal as well as spatial resolution? Is that any possibility that in future high resolution could prove some of the non-white light flare to be white light flare?
Recently, just a few satellite has a white light observation band. So still we have the SDO HMI, but in future maybe the ground-based observation is measured, I think.
Yeah, and my second question is there any simulation attempt to segregate from this white light and non-white light flare and just to see what the basic mechanism is different from white light flare to non-white light flare?
So there is many models to produce the white light emission, but so I think the mechanism, we can tell the difference of the mechanism from the white light or non-white light flare. I think that is just the strength of the particle acceleration is just depending on the production of the white light emission.
Oh, so other basic mechanism are basically same, only this length you are saying makes the difference.
Yeah, I think so.
Okay. Thank you very much. It was a nice talk. Thank you.
So yeah, shall we ask Vinod to go ahead? I think she had a question. Vinod, can you please unmute and...
Okay, can you hear me?
Yeah.
Yes, go ahead.
Yeah, Professor Watanabe, very nice talk.
Yeah.
And I have a question. See, the basic source of energy is the keV electrons, right?
Electrons, so hard X-rays.
The main source of energy for all types of emissions is the keV electrons.
Yeah.
Right?
Yes.
Yeah, so I was wondering if it is possible to approximately estimate what fractions of energies are distributed amongst the hard X-ray, soft X-ray, microwaves, and white flares.
Yes. So but energy of the white light emission can be explained by only by the by using the accelerated electrons. That can be explained, but some other candidate also think about the origin of the white light emission. So that is also not yet cleared.
Okay, thank you.
Thank you.
Okay, I see there are no other questions. So I think we should thank Kyoko and also to all speakers of this session. Thank you for the interesting talks. And now I will hand it over to Piali to say the final words.
Yeah, thank you, Vaibhav. So once again, I mean, since we could not attend to all the questions, I would request the speakers to also check the Slack channel for any more questions from any of the participants. So with that, I think we can close this session. Thank you to all the speakers and the participants. And we will reconvene at 10:30 with the second session, high resolution observations of the chromosphere. So thank you, everyone. See you at 10:30. So that will be around 20 minutes from now. So see you in 20 minutes. Rajguru, do you have anything to say?
Yeah, so the speakers for the next session can start checking their presentation. So we meet after 20 minutes at 10:30. The speakers of the can stay on and try to check their presentations.
Yeah, please, yeah.
Madras Observatory was shifted to Kodaikanal. Professor Mitchie Smith undertook the Herculean task of setting up a dedicated solar observatory Regular observations of the sun began by the early 1900s. White light images of the sun were taken consistently since 1904 using the 6-inch telescope mounted in the north dome of the observatory. Soon, the interest grew in observing the sun in calcium K and hydrogen alpha spectrum.
This is a spectroheliograph. This is an instrument used to study the sun in monochromatic light. So after the discovery from E. Halley from 1904, this instrument has been here taking the observation of the sun in calcium K as well as H alpha.
John Evershed joined Kodaikanal Solar Observatory in 1907 and used the spectroheliograph to discover that there is a radial outflow of gases from the sunspot. This discovery was later known as the Evershed effect and was a major milestone in the history of the Kodaikanal Solar Observatory. The Kodaikanal Solar Observatory has a rich history of taking solar images in calcium K, hydrogen alpha, and white light on photographic plates and films for over a century, making it one of the only place in the world to have such important data set. Every morning, the telescope operator mounts a fresh plate and exposes it to capture the disk of the sun. The plate is further taken to development lab where the negatives are developed using several fixation techniques. These photographic plates and the films containing the solar images have been stored carefully in individual paper envelopes in the archival room, which is maintained at a particular temperature and low humidity conditions for better preservations. Realizing that enormous useful information can be further extracted from the solar archives, efforts were made to digitize the plates and films using state-of-the-art modern instruments. A digitizer unit has been set up at the observatory to digitize over 100 years of solar data. The unit consists of a uniform source sphere of 1 meter in diameter with a front mouth opening of about 35 centimeters. The photographic plates from the archival room are carefully taken out, cleaned, and polar aligned corresponding to the date. The plate is then mounted onto the slider and the overhead CCD camera
If anybody has a question. Okay, sorry. Yeah. Hello. Hope you are there. That's my voice is very low. Okay. So, Arunashwati. Indiana is there.
Hey, hello Nagaraju. How are you?
Abhishek, how are you? Good.
Nagaraju, good morning. I hope my voice is coming to you.
Probably because you removed the mic, removed the earphone, so more noise is coming now. Just now you probably removed the mic. Yeah, yeah, okay. Okay, just yeah.
Speaking to me.
Yeah. I was speaking to you. Yeah.
I am check. Okay. Just a minute more. Jenna, you can share your screen. Welcome to this session on high resolution observations of chromosphere. In this session, we have 5 talks. One is of 30 minutes duration. Okay. So the first talk is of 30 minutes duration, and remaining 4 talks are of 15 minutes duration. And we follow the same rule, like 5 plus 5 for the 30 minutes talk and 12 plus 3 for the contributed talks. Yeah, so the first talk is by Gianna Fauji from NS4 USA on chromospheric magnetic fields and dynamics.
I'll just try to add that after when 3 minutes are left, I will try to give a signal before the end of the talk. Okay.
Yes. Okay. Thank you. Please tell me if you see the presentation or my view. You know, I have 2 displays and they all.
Yeah, this is still your view, so you have to swap the display in order to.
I will. How about now?
Yeah, now it's clear. Oh, okay, please go ahead.
Okay.
Thank you.
Thank you very much. Thank you everybody for, well, thank you to the organizer for inviting me, and good morning to everyone, and good evening and almost good night to a lot of us, including myself. So I'm Gianna Cauzzi from the National Solar Observatory in Boulder, Colorado. The original title of this talk was Chromospheric Magnetic Fields and Dynamics, but since Alphonse was talking just before me, I feared that we would be overlapping somewhat in our topics. And so I decided to give a little different spin to this. And I will be talking more about the thermal structure of the chromosphere as well as magnetic fields. So in a sense, it's a bit of a different talk, and I'm not talking about particular phenomena, but more about the diagnostics and some of the interesting progresses that have happened in the last years. So just a quick, or maybe not so quick, summary about the chromosphere, which is, as you all know, a very interesting and very complicated part of the solar atmosphere, because it really is an interface between the quiet photosphere and the very magnetically dominated corona. So in terms of diagnostics in the visible, we are not very lucky, because the chromosphere is essentially transparent in the visible. And really we're left with only a few strong optical lines that have enough opacity to be, to sense the chromosphere, the tenuous chromosphere. So there is the Palmer series of hydrogen, there is the calcium-2 resonance at the HNK, as well as the subordinate triplet at 8500 angstroms, the helium triplet at about 1 micron, and so on. Of course, there are diagnostics in other spectral regimes, but they are a bit more difficult to observe. In particular, we have some lines of the CO at 4 microns. Then those that have not been observed since quite some time, since the MacMath went offline, and hopefully with the KIST coming up soon, there will be an instrument that can actually do this at a fairly decent resolution. So that will be very interesting to see. Then there is some radio continuum, and I will be talking about it in a little bit. And of course, as you all know, there is a lot of diagnostics in the UV, and that, however, requires that we go up in space, which is expensive and certainly not real. The unfortunate reality is that all of these diagnostics require non-equilibrium analysis, because the chromosphere is so tenuous that really thermodynamic equilibrium does not hold. Most of these diagnostics provide sense the magnetic field, but unfortunately, again, the polarization signal is weak, and we'll get back to that. So what kind of requirements do we have? The fact that the magnetic field becomes important in the chromosphere and start expanding and becoming more horizontal requires that we actually observe a large field of view, because really things might be connected to something that is not exactly nearby, right? So that we have to be aware of that. The higher resolution is obviously something that we are striving in all of our efforts, and we have to be very, very aware that we really need a very high signal to noise observations for doing polarimetry in the chromosphere. So in a sense, we are in a photon-starved problem, that it is why we try to get larger and larger telescopes. So let's start with the chromospheric temperature. That seems like a trivial question, but it really isn't. And of course, we know that in general, it's 7,000–8,000 Kelvin and so on, but how it is structured, the exact values as well as how it is structured in space and time are certainly things that are not fully understood yet. Despite the fact that, as I just said, the chromosphere is in non-equilibrium, there are a few diagnostics that maintain a certain coupling to the local conditions, in particular, and the temperature. In particular, we're talking about the core of the calcium-2 lines, both the resonance lines and the subordinate triplet. And here you have an example, on a very quiet area in the photosphere, you see there is just about nothing. And the picture in the core of the calcium-2 line that shows that is a proxy for temperature, as line formation tells us. You show a very different picture where you have certainly some magnetic elements that are sort of identifiable because they are bright, but they are also sort of somewhat diffuse, and we'll get to that. And some other, for example, these little tiny bits here in the quieter area that actually are the signature of acoustic shocks that happens in a very quiet chromosphere where there isn't magnetic field. In the work some years ago, we actually pushed this idea of this diagnostic by by doing a joint analysis of the calcium-2 and the H-alpha line. The H-alpha being the chromospheric line for excellence, but it is extremely difficult to understand. It's got a very complicated formation. However, the reasoning was that hydrogen being the lightest element that we have, it should be somehow sensitive to temperature via thermal motion, so that the width of the line maybe would be a good indicator of temperature as well. And it was rather interesting because you see that, the general sense, these two things are very well related. And if you actually, this is one particular instance in time, if you actually collect a lot of data all together, you obtain something, a very clear relationship between the two diagnostics. And in this paper by some time ago, we really ascribed this correlation to the effect of temperature. Now, we could derive, using a lot of assumptions for what concerned the line formation of both lines, we could derive an analytical formula that would sort of calibrate such a curve, that is, provide a temperature for, a certain value of the width of H-alpha. That was a bit, shaky. We would have some numbers fairly high, some, values of maybe 40 or 50,000 Kelvin. That might be a bit, maybe difficult to believe, but we'll get to that. How does it look? How does this thing look at the larger scale? So this is a very large active region. This is about 4x4 arc-minute field of view at a very high spatial resolution, sub-arc second, well sub-arc second, because this is actually a mosaic of 9 different field of views. But anyway, so you see the very variegated structure. And again, you see that certainly you have brighter and what we think are hotter parts where we know that there are magnetic fields, although we still don't know exactly what is the mechanism that determines the heating in these particular areas. We see those little bright points that I was pointing out before in quieter area that sort of peek through these other fibrils. And indeed, the very striking feature in these images is of very, darker, long, thin features that we call fibrils, and that we think outline the magnetic field lines, although we are not sure of that either yet, and we'll get back to that. If we go to the H-alpha width picture of the same field of view. And I'm sorry for the rotation. I didn't find the proper image. But anyway, this thing is even more striking. And I think that what strikes me most is the fact that not only what we know is the magnetic areas, at least in the photosphere, not only those areas are bright, but also the beginning of these fibers that I was discussing before, they appear to be almost as bright as the magnetic elements. So they must be hot and so. And I think that essentially there hasn't been much work done on this since, but for example, studying the spatial temporal distribution of these things, that would be extremely interesting. For example, they could be related to the spicules the spicules are the type 1 spicules that Alphonse was talking about. So since a few years, we have a much better tool to sense the chromospheric temperature, and that is the continuum observed in the millimeter range with ALMA. ALMA, as you all know, is an interferometer working in Chile. It's a very big instrument, so it can observe the sun with a decent resolution. This is an observation in band 3 that corresponds to about 3 millimeter wavelength, and this has a resolution of about 2 seconds. Of course, we could observe the continuum, the radio continuum even before, but with smaller instruments, the resolution was really poor. And the good part of this diagnostics is that it is really a linear thermometer. The continuum in this wavelength is 4 million TE. And since we are so far in wavelength in the radio, it actually becomes a linear relationship between the intensity and the temperature. So this is the temperature of this particular area that if you ask me, I wouldn't really know what kind of area it is on the sun, but since we had the magnetic maps, this is small magnetic network element with some plage on both sides of the field of view. But anyway, so we have values that are that can go, of the order of 7, 8, all the way to 12,000 Kelvin in this particular kind of area. So if we go back to our study that I discussed before, and we compare this. Sorry, this doesn't work. I don't know why. I'll go there. Oops, too much. If we compare it with H alpha, and in particular the H alpha width, so this is just the intensity. Of course, the ground-based data that we obtained in coordination with ALMA have a much higher resolution, spatial resolution. And, just looking at this, it wouldn't be obvious to me, at least the first sight, that we're looking at the same field of view. But once we go into the width of the H alpha line, things become extremely, to me, it's very striking that this thing really looks a lot like it. And if we degrade the resolution of the ground-based data, I think that I don't need to convince you that we're looking at the same thing. And not only that, but it appears that indeed the H alpha width seems to be a very good indicator of the kind of temperatures that we can have you can find in the chromosphere. And actually, if this holds, if this correlation holds, for example, in other kind of field of view with more active or less active and so on, there will be a very nice tool to use, for example, to do some kind of studies at very high temporal resolution or such. And by the way, this is all work by a student here, CU Momchil Molnar. So we're very pleased, although there is a question that remains, at least in our heads, that it was, okay, we have this great correlation, but why is it that we have it? The ALMA, I just told you that it is the great LTE diagnostics. How does it work that it correlates so well with H alpha, which is certainly not an LTE diagnostics? And again, in the paper, it's discussed pretty well, but the bottom line is that the both diagnostics critically depend on the electron density. And while it is true that the continuum is formed in LTE, the number, the electron density itself is not, because it depends on the rest of the atmosphere. And so you have a clear sense of the temperatures with ALMA. And what you don't have is a clear, fixed height at which any given wavelength is formed. So as much like the calcium-2 or the H-alpha or magnesium, the height of formation can vary greatly in time and space. And there is a recent paper by Juan Martinez Sicora, which is very, very nice, and that discusses the formation of the ALMA millimetric continuum in the sun, of course. So we continue then into in our line towards better and better diagnostics, because here, we get the very nice temperature, and certainly it is at only one place in the atmosphere. We still don't know which one it is, but it is. We know that it is one. Recently, I think this is something that has become of age. This is something that we knew how to do it many, many years ago, but now has finally come of age because of many reasons. And it is the spectral inversions that essentially is that you start with gas model of your whole atmosphere, and that means the whole stratification of the atmosphere, and you synthesize the spectrum in that atmosphere, the lines that you're interested in, compare them with the observation, and repeat until you get a nice match. So certainly these things works as long as you have cleared the physics that produces your spectral lines, your diagnostics. And in the chromosphere, that is certainly not trivial. Particularly these codes, these inversions have to work in on LTE. Some of them have to take into account the partial frequency redistribution. And because of this, they are usually limited to 1D, because otherwise the problem becomes prohibitive in terms of computing time and so on. They can use multiple lines to be used at once, and actually these plots on the left are from a paper from Da Silva Santos that was really testing that is checking how well the inversions would work depending on which lines you would use for the inversion, which combination of lines, and so on. And so you have your typical suspects. You have the magnesium lines, the calcium to K, the 8542, then you have the photospheric lines, and they actually used also the ALMA continuum at 1 and 3 millimeters. These are 2 different pixels, by the way. And so the point of the paper was that of comparing, to see what was the best combination of lines that you should use. And the results were that, if you use only one line, in particular only the 8542, you have a result which is not so doesn't so well reproduce what is your reality, which in this case is a model. You can see this dash line here. And that makes sense because the line is formed a little lower than all the other diagnostics, and so it cannot sense the top of the atmosphere as the other lines do. So there is a lot of papers that are coming out using these codes, and actually I wanted to mention them by name. Maybe most of them, Nicole, Stick, and Snappy. And I wanted to mention also this Desire one, which is a project of Hein Wojtenbroek here. So because this will be used in the pipeline for the data reduction of the KISS or the spectrographer, so it will be used to produce level 2 data. So a lot of papers, are coming out with results of this kind, and I like to show a little this one in particular because they looked at the temperature stratification in some of those bright fibrils that I was pointing out that extrude, if it is a word, if they go out from the magnetic footpoints of the network. So you might see all these little lines that identify some bright fibrils in the core of the calcium line. This is the calcium 2K. And this is a typical temperature stratification. So you go from the bottom higher up in the atmosphere, and the red is the fibrils and the black is the background. And you can see that these things do become, on average, hotter than the background, but not by much. So in a sense, this is not consistent with what I showed you with the ALMA and the H-alpha analysis that had the temperatures that would go up to 10 or 12,000 Kelvin, and here we stay barely, between the 6 and 7. So that's something that is certainly ripe for some more work. Oh, obviously, late. But I wanted to mention this other thing, which is, I think, is a very, very important development, recent development. That is, once you do these inversions and you have your model atmospheres, one thing that you can do is to calculate the radiative losses because the chromosphere cools via radiation. So this is where most of the energy, where the chromosphere loses most of the energy. And for whatever mechanism you want to work to heat your chromosphere, to deposit energy in your chromosphere, it needs to deposit at least the same amount of energy that you're losing by radiation. And amazing but true, since the mid-70s with the very famous Whitbread and noise analysis of the canonical values of 4 kilowatt per square meter in the quiet sun and 20 kilowatt per square meters in inactive areas, that everybody uses, there hasn't been much after that. So this is a very recent paper, is actually not yet published, I think it was on arXiv, that they do just so. And this is an emerging flux region, and it's extremely interesting that in some parts of the region, they actually find values of radiative losses that are many, many times the canonical values, the order of 6, 7, 8 times larger. So that's very important and very important constraint, and I hope there will be many more works of this kind. This is another one. This is from the group in Ondrejov. They did essentially the same kind of analysis with different data, and they wanted to test a different idea, but anyway, but the sense is the same. Okay, I better hurry up and getting now to the measurement of magnetic fields in the chromosphere. So we know that the magnetic fields are extremely important. I've mentioned it several times, but unfortunately, up to now, we really have a little sense of how strong are these fields, in which features, how are they oriented, does this change in time, and things like this. And the bottom line is that they are very difficult to measure because the signal is very low. So again, the calcium 28542 seems to be the perfect line to measure also magnetic field, at least in the middle chromosphere. And just to give you an idea, this is just a snapshot of a measurement with a filter instrument, so that you have images in the Stokes parameters, I, Q, U, and D, just to give you a sense of how distributed, variegated is the spatial distribution of the polarization. But the important graph is this one, because even near a spot, if you can read the y-axis here, you see that the Stokes parameters are just a few parts per thousand in terms of, a few percent if you're lucky near a spot in the circular polarization, but a few parts per thousand in the linear polarization. So you realize that this is a very difficult problem for the observation, from the observational point of view. And this is about the best that we can do today. Of course, that's because we want to maintain our resolution. This is done with a cadence of about 20 seconds, if I'm not mistaken, and with a spatial resolution of about 0.1 arcsecond per pixel. Of course, if you integrate over a larger area, but obviously you don't want to do that because we know that at the small scales, we have a lot of interesting physics and phenomena, like alphas and Schoenberg, for example. So again, how do we go about by measuring the fields? Let me see, inferring the fields rather than measuring, because we measure polarization. And much as I explained before, your inversion are your friends in this case as well. Those same codes that I mentioned before can also invert or reproduce not only intensity, but also the polarized profiles. And this is an example by Jaime de la Cruz when he described his code at the stick. So you start from a model. This is, you see the stratification of temperature, velocity, and magnetic field as you go from the photosphere up to the middle chromosphere. And these are just different ways of, setting up the inversion and so on, just to see how that works. The important thing is that you have a stratification. So that you have information, at different heights, and you can, for example, address how the field expands and so on. And here are some very recent results. Actually, it's the same paper that I mentioned before, Diaz-Bazos and the one of the radiative losses. And so that you see that this is the longitudinal field in the calcium 2 line, this is the transverse, and the contours are the photospheric fields. So you see the transverse becomes being present, very well discernible away from the photospheric footprints. Unfortunately, this is a very expensive way to go about the problem, because computationally these things are very, very heavy. So really you cannot do a lot of pixels and a lot of temporal sequences and so on. We're fortunate
Gianna,
that,
3 minutes, please.
Okay, I'll try to go very fast. So I will not go through the formula here, but in the chromosphere, we're fortunate that we can use the weak field approximation in many, many cases. You can use it when the Zeeman splitting is smaller, sensibly smaller than the Doppler width of the chromospheric lines. And you can imagine that this condition is satisfied in many cases. And so the weak field approximation that gives you a direct relationship between the Stokes parameters and the field has been used recently and abundantly, I would say, in many works. For example, measuring the plasma magnetic field. This is from the Stockholm group. So they had different lines, and you see that if you go from the photosphere all the way to the mid-chromosphere, the field becomes less intense and also more diffuse. Although the plage still shows fields of the order of 400 Gauss or so. And the signal was not enough to do the transverse the analysis of the transverse field in the calcium, but they could do it for the magnesium, which is an intermediate line. And you can see here is the transverse component, and this gives you the inclination. So you see that you start getting these brownish colors that show that the field is becoming, certainly deviates from the vertical very much. I will skip this because I want to get to another one later. Again, back to Alphonse's talk, the magnetic field of Spicule is something which is coming up, and this is very exciting. So these authors actually had very high spatial resolution and temporal resolution, which seems to be necessary to find this kind of results. In particular, they have fields, again, only longitudinal because there isn't enough signal for the transverse component, that are well over 100 Gauss, and actually for some of these spicules, especially closer to the limb, they can be certainly much higher than that, of the order even of 300 or 400 Gauss. This is, this is in contrast to some older results, which are actually not so much older, of 5 years ago, that found values of many, 3 or 4 times less. And probably the spatial and temporal resolution is a great factor. I wanted to show this because they use a different line to measure the magnetic field, which is the helium-1. The helium-1 at 1030, and again, I will not go through all of these words, but this is another very important line to go and measure the field in chromospheric features, especially for something like prominences and filaments and so on. Because the line is fairly sensitive in those situations. And nice result by Tom Shad a few years ago was that of checking the alignment of those fibrils with the magnetic fields, which I mentioned before, that we still don't know if it is true. As far as I know, there are only 3 papers that describe this. And the answer is yes, but, and there is still some sort of scatter of 10, 20 degrees, which is not clear if it is due to noise or not. And also some very nice work a few years ago, again, from Tom Shad, that measured the magnetic fields of coronal rain. This, if you have a chance, try to read this paper because it's really, really fantastic, I would think. And they derive a field which is fairly strong. It can be up to 400 Gauss or so, all the way to 25, 30 megameters above the surface. And so I think I will stop here. I think that you've got a sense of our quest for doing even more sensitive observations if we want to go and have even more information on the magnetic field. And we've just started, really, but I think there will be a lot of big progress in the next few years, and especially with new instruments coming online. Thank you.
Thank you very much for the nice overview about the chromospheric observation and especially about the magnetic field observations of the chromosphere. It's time for questions. One or two quick, please.
Yes.
Raise your hands.
Sorry, I'm always long. Sorry.
No, it's okay. I see the hand from Tanmay Samanta. You can unmute yourself and ask the question, please.
Yeah, nice talk. So in the calcium 2 images you showed, there are a lot of brightening randomly, even below the dark fibrils. So are those really chromospheric structure, or are we looking at the photospheric bright point?
No. Those are chromospheric. Those are the acoustic shocks in the chromosphere.
And what is the reason of the foot point brightening? Like the motors, they're more brighter, or the fibrils or spicule, whatever you say, which are coming from the network region, why they are more brighter at the foot point region, not at the top? So if they are due to shock, they could be
I don't have an answer for you. I think that they might be related indeed to the magnetoacoustic shock that the Hanstein et al. Or the dynamic fibrils and or spicule type 1, whatever they're called, right? So that at that point you have some dissipation of energy that would increase the temperature. Why it is only for a certain portion of this fibril, I really don't know. And I think, I think this, is a field where there's a lot of work to do. It's just that nobody does it. They don't have time or something.
I see the next one from Hui. Please, you can unmute yourself and ask the question.
Okay, so very nice talk. You show a plot. I see there sort of a scatter plot between the temperature derived from normal observations and also the width of the H-alpha line, right? But we know that the H-alpha line is not always symmetric, and sometimes, and actually very often, we see the asymmetric H-alpha line profiles, which might be caused by some jet-like features or spicules. So my question is whether these dynamics can affect this correlation.
Probably. And if you, maybe you don't notice it in a quick talk like this, but there are a lot of places in the plage, especially, that they seem like pepper and salt because the line there has strange features like the ones that you're discussing, right? Mm-hmm. So if it is just shifted with the map of the width, take that into account. If there are asymmetries, those are sort of, it's an average parameter in a sense, yes. Okay, I would think that this is valuable for an ensemble kind of analysis rather than every single pixel by itself.
Mm-hmm. Okay, thank you.
I guess thanks for the talk and thanks for the nice questions and keeping it in time. The next in line speaker is Tanmay Samanta, who will be talking about the generation of solar spicules and subsequent atmospheric heating. So Tanmay, it's over to you now.
Arun, just a moment. There's a question from here in auditorium in IA.
I see. Okay, please go ahead. Yeah.
Gianna, it's a nice talk. So I just
thank you.
Yeah. I just wanted to inquire the temperature structure that you determined from the helium-1 and the calcium-2 and the magnesium core. So is it comparable or how it is from the non-LTE inversion core, right?
No, for the little bit that we've seen, not necessarily. No, there was the paper that I mentioned that was from, I forgot the first name, starts with K, but no, they found an increase in temperature from inversion that was very modest. That didn't quite seem comparable to what the H-alpha would say. It's a cascade. The H-alpha would say so, and I trust it because Alma said so, right? So no, I think there needs to be investigated.
But is there any reference to check whether it is giving the right temperature?
Inversions are in a sense the most reliable. Then there is a lot of issues also with inversions. There is an ambiguity between microturbulence and temperature that is intrinsic, and you sort of, solve it as well as you can. There is the fact, and might be important, but the fact that the inversions do not consider non-equilibrium ionization, which might be important.
Okay, thanks.
Any other questions? Okay, then we can move on to the next talk by Tanmay.
Okay, Tanmay, over to you, please.
Hi, good morning, everyone. My name is Tanmay Samanta, and I'll be talking about generation of solar spicule and subsequent atmospheric heating. Currently, I'm at NASA's Masters Space Flight Center working as a postdoc, but I did this most of this work at Peking University. These are my collaborators. So since Alfonso already have talked about a lot about spicule, and also Gianna have talked about a lot of chromospheric dynamics. So, and Alfonso have already shown some of the results from my work, or like our work. So I'll go a little bit deeper into this spicule formation mechanism, and if they're responsible for heating of the solar corona. So what you see here, there are a lot of these dark jets coming when you look at the chromosphere in H alpha wing. So you see a lot of this spicule like jet-like structure coming from the network region. So those bright point below bright areas are the magnetic network region, and a lot of this jet-like structure appear from these regions. These are sometimes called network jets. That they have many different names, as Alfonso pointed out. They're ubiquitous jet, mostly coming from the network region. So these are known as spicule, and also different name, like in terms of where you are seeing, at which telescope and which filter are you seeing, and what wavelength. They're believed to be important for coronal heating and mass supply. So they're very, very important to study. So there are around 1 million of spicule present in the sun at a moment, and mostly coming from the network region. Here is a movie again showing the H alpha blue wing, and you see this lot of jets are coming from this bright network region. If you have a closer look at the network region from the Swedish Solar Telescope, which is 1 meter telescope, you'll notice that the magnetic field in this region particularly shows kind of unipolar. So these jets have a lifetime of 10 to hundreds of seconds, and they have speed of like 150 kilometers per second. And they are mostly coming from unipolar region. So there are many proposed mechanisms of spicule formations. I will not go into details. Alfonso have already mentioned some of the mechanism. So there are, I will say there are a lot of proposed hypotheses. So there are magnetic reconnection. There could be different kind of magnetic reconnection. There could be Lorentz force, interaction between ions and neutrals through ambipolar diffusion, microfilament eruptions. And there could be P-mode shocks, alpha and vortex flows, nozzle flows, magnetic wraps. So this will not require a opposite polarity magnetic field or magnetic reconnection in this kind of case. So we notice that there are many theoretical and numerical studies, but still direct observation of the formation process is missing. What I mean by that is what is happening in the foot point area of the spicule, we really don't have a really high resolution observation. So mainly due to high insufficient resolution and sensitivity of existing telescope. So evidence for the formation mechanism of spicule can be provided through simultaneous high cadence, high resolution observation of both the photospheric magnetic field and chromospheric dynamics. And here we did this observation with the BBSO Goody Solar Telescope, which observed the photosphere and chromosphere at high resolutions. They have also a magnetic field measurement instrument, which particularly look at deeper photosphere at high resolution compared to the other available instrument. And also we use SDO's 171, which has much lower resolution compared to the H alpha observations to find out whether this spicule can influence the corona. So here is a multi-layer plot. What we see here, these middle two panels are like shows chromosphere and photosphere, and the top panel corona. So to understand this formation mechanism of these spicules, we really need high resolution magnetic field measurement. And here is a comparison of what we see from the SDO HMI. So we see this this region is mostly unipolar, but when you look at the GST magnetogram, we see there are a lot of opposite polarity around this network region. So the magnetic field measurement in the Queensland region is quite challenging, and so the BBSO has this NIRIS instrument, which measured the full strokes IQUV. And here we saw in the left-hand panel is longitudinal flux density, which is kind of vertical magnetic field. And right-hand panel is show net linear polarization, which are particularly showing the horizontal magnetic field. And these horizontal magnetic field are important to understand the flux emergence processes in this area. So the iron 1.56 micron has a effective Landry factor of 3, and its long wavelength provides an advantage compared to the optical lens in measuring the weak field in the interactive region. So there is a talk by Luis in the next session, and I think he will be talking about this magnetic field measurement in the question in details, and the flux emergence, flux cancellation, and all the stuff in the question region. I'll not go into details. So to understand the formation mechanism, the key element of magnetic field, and we have derived this magnetic field from the NIRIS instrument at GST. And here is a binary map, particularly showing the 10 Gauss magnetic field at this region. Though ground-based observation have a lot of noise, so we have to be very careful, and a lot of effort goes on to find the real magnetic element, almost real, or whatever we say, with some certainty. And then we overplot this magnetic field on top of the H alpha images, and red and green color shows the two different magnetic polarities. So they have around 10 Gauss of magnetic field. And you'll notice that the cadence of the magnetic field is around 20 times lower than H alpha observation. So that's why they move a little slowly. And also the resolution is a little lower than the H alpha observation. So these are the limitations. So after the overplotting this map, we check the movies in details, and how do we find that there are enhanced specular activity. So in B1 to B9 panel, we see there are a lot of dark jets. They're occasionally occurring at the several spicule originate simultaneously from a small region, and we call them as enhanced specular activity. And we notice that at the foot point of this enhanced specular activity, there are opposite polarity magnetic field present at the time of the generation. So the enclosed black circle shows the location of the red polarities at the foot point of this enhanced specular activities. Here is a movie what is showing in the left hand side is showing the zoom view of the foot point area of the spicule generation location. And you can notice the network field is again represented by this green color, which is around kilogauss of order. And there are opposite polarity red color magnetic patches which have a field of like 10-20 Gauss. They come close and cancel with the magnetic opposite polarity magnetic field. And at the same time, there is generation of this small scale or like enhanced specular activity. So here is another example. You can notice there is a generation of spicule from this network region, or we say from the bright point. And we can notice that when the unipolar field are present all the time, which is kind of represented by the green color from which covered the magnetic bright point, there are not many spicule coming. But when there is a flux emergence, the flux emergence also can be seen from the breaking of the granules, and also the linear polarization, which is not shown in the plot. If you can check in the paper. So there will be linear polarization appears, and there will be flux emergence, and at the same time, we see the generation of this enhanced specular activity. So they are driven by opposite polarity, presence of opposite polarity magnetic field. And again, we notice that there are many individual spicule, many of them are present. When we look at the foot point region of this small individual spicule, we see that there are opposite polarity magnetic field present at their foot point. So these are again, blue circle marks the location of the foot point, and you see there is opposite polarity magnetic patches, which is represented by red color contour. They're present at the time of their generation. So the many individual spicule also originate from the small scale opposite polarity magnetic flux near the network field. And here is a location, the inner yellow boundary shows the boundary of the inner yellow circle shows the boundary of the network, and outer circle shows the 3 megameter distance from the network. And what we notice from in this movie, that most of the magnetic field of this weak magnetic field in the internet region, when they cancel or they emerge within this region, they produce this spicule. When they are very far, they generally don't produce spicule. And we measure the kinetic energy of the spicule and also the magnetic energy at the feet of the spicule, and the calculation suggests that there is available magnetic energy sufficient to drive spicule. So So we almost studies all this spicule in these 10 minutes of data in details and check what is happening at their foot point. So what we find that almost all the enhanced spicular activity, the large one or the one which are multiple of them are coming from a small region at the same time, are associated with the emergence of or appearance of opposite polarity magnetic flux and subsequent flux cancellation near the network boundary. There are many individual spicule also originate from the small scale opposite polarity field near the network field. For some small spicule, no opposite polarity is detected because the magnetogram have a spatial resolution 3 times lower and cadence 20 times slower than the H-alpha images. There may be small scale or highly dynamic field at the foot point of this small spicule that we are not able to detect. So we need larger aperture telescope. Probably DKIST can help in this area. Also notice that 2/3 of the opposite polarity magnetic element with the outer yellow circle are associated with generation of 1 or more spicule during their lifetime, and the remaining 1/3, mostly small size, do not produce noticeable spicule. And some may represent low-lying element that fail to interact with the overlying network field. Also, very small or weak element may lead to very small scale spicule that cannot be resolved with GS resolution and sensitivity. So we need larger aperture telescope again. So here is again a picture snapshot of this network region and the spicules. And in this cartoon area, we saw that this small scale, again the darker circles, darker small circles represent the network bright point, and the strong magnetic field of kilogauss present at this bright point location, and they expand in the chromosphere. And when there is opposite polarity magnetic field emerge, they reconnect with this overlying loop and they produce spicule. So spicule orientate from the location of opposite polarity magnetic field, that is our observation near the strong network field of kilogauss. Furthermore, there are some studies where they show that inverted wave shapes are found at the feet of chromospheric jet or some spicule. And also we found the explosive event, which are kind of manifestation of a reconnection at the foot point of the network jets in the chain et al. 2019 paper. She strongly suggests the reconnection origin of spicule. So in terms of corona response.
And my 3 minutes, please. Okay.
So in this image, we saw a running difference image of the chromosphere and the corona from IRIS and ISDO instrument. And what we notice that in the limb, the spicules, when there are large kind of spicule presence, they influence the corona, and we see something propagating in the corona at the same time. So this kind of connection are found in many papers in like last 10 years. There's a numerical model suggests that the small scale activities could influence the corona or could energize the corona. But it is not clear why some spicules show signature in the corona where others do not. So here, again, we focus on the enhanced spicular activity, the larger one, the one which produce a lot of them at the same time, they're covering a larger area. And what we find that almost all of them produce coronal emission at the top of at the top of the spicules. So in this red rectangular region can show the time instances where this presence of this enhanced spicular activity, and we can notice at the top of this enhanced spicular activity there is a emission from 171. So it is not 100% clear if these are really coronal contribution, and Aditya VLC probably will contribute in this area when you are particularly observing in the limb. So here is again a snapshot where it's showing the enhanced spicular activity and on top of that we overplotted the AIA 171 image, and we see this strong emission. So most enhanced spicular activity shows coronal counterpart. Coronal heating event caused by spicule are very common, and coronal signature of small individual spicule are hidden in the noise or unresolved by AIA. That's what we think, and with high resolution instrument, we probably will see a lot more. So here is the conclusion: around a few million spicule present at the sun at a moment, and our observations reveal that magnetic reconnection event at the network boundaries can drive spicule and produce hot plasma flows into the corona, thus providing a link between magnetic activities in the lower atmosphere and coronal heating, and difficult to observe spiculated corona emission for all of them. Probably we need better 3D model to understand the process completely. Thank you.
Thanks for the nice overview about the chromospheric spicules. It's time for questions. Please raise hand, and I request Dr. Nagaraju to see if there's a question in the auditorium.
Yeah, I'll check. Any questions here? No question from here. Let's
Okay. Okay, great. So I think there are no questions in the online audience as well. So we can move on to the next speaker of the session.
Wait. Just a minute.
Okay, sure.
There's a one raised hand from Kamalesh Bora.
Yeah. Okay. Kamlesh, you can unmute yourself and ask question.
Yeah, hi, this is Kamlesh from Udaipur Solar Observatory. So actually, I have a question regarding this network bright point. So you have network bright point and chromosphere, right?
The network bright points are they're called magnetic bright point. They're mostly photospheric structure, as in literature people define. Of course, they have signature in the chromosphere.
Okay, so like you mentioned that the reconnection must be occurring at the boundaries of the network bright point, right?
Yes.
Yeah, so actually I have this basic doubt. How would reconnection occur in like photosphere and chromosphere? Can you tell me in terms of the magnetic Reynolds number? Because I think the plasma is not well frozen there with the magnetic field and flows are very strong. So how would reconnection occur?
So of course the reconnection is not, we think that reconnection is not occurring at the photosphere. So flux cancellation are happening in the photosphere, or what from the observation we term as flux cancellation, what we observe in the photosphere. So we think that when we look at the linear polarization, so we find that first linear polarization appears, and after that there are vertical magnetic fields. So after a few minutes, so it takes the field to come from the photosphere to higher height to reconnect with the overlying magnetic field. So we think that the reconnection is happening in the chromosphere, not at the photosphere. And I'm not sure about the magnetic Reynolds number. I think we need to check that.
Yeah, actually it is like a bit, what to say, I feel it is not safe to say that reconnection occurs in the chromosphere or something, because we need to then look for the magnetic Reynolds number and what is the, how the frozen in condition is broken when we are talking about the reconnection. So like
there are a lot of models shows that the reconnection happening in the chromosphere and producing jets. I can also show this.
Okay. Then we can talk. Yeah, I can know.
Yeah. Thanks. And just one question from here in the auditorium. Processing. Please go ahead.
Nice talk, Tanmaya. You told about chronal features related with the spicules. At what temperature do you observe that chronal features?
So the AIA 171 capture around 0.8 to 1 million Kelvin temperature. And this brightening are also seen in 193. So there are around like coronal temperature of 1 to 2 million Kelvin. And in the limb, probably the spectroscopy observation of iron like 10 lines could probably 11 lines could from Aditya could capture this emission.
Thank you.
Hello?
Okay.
Hello?
Oh, yes, please.
Can I?
Okay, a quick question, maybe.
Yeah, short one. You mentioned magnetic flux cancellation time of 3 minutes.
Yeah.
Can you identify it with any physical time scale or characteristic time scale in the region?
I'm not sure about the characteristic time scale of the region. Probably the P mode I don't know if they're related to P mode or the flow speed of the region. I'm not sure. We probably need to look at that. So maybe I'll talk to you later. I have some questions.
Okay. Thank you.
Okay, Arun, we can move on to the next talk. We are running short of time.
Okay, thank you very much for the questions. And we can move up to the next talk, which is by Jen Jacob about the torsional motion and short period oscillations in equation prominence. So Jacob, you can start.
Am I audible?
Yes, yes. Go ahead.
Can you see my presentation?
Yeah, it's fine.
Okay. Good morning. I am J. PT, research scholar working under the guidance of Dr. Ramajur Maurya, Department of Physics, National Institute of Technology, Calicut. I express my thanks to the organizing committee of Conference on Magnetism and Variability for giving me an opportunity to present my work. I am here to give a talk of my research work on torsional motion and short period oscillations in a constant prominence. Overview of my work. In introduction, I will explain what is prominence and the motivation of my work. Second, observational data used for analysis. Next, I discuss about the plane of sky motion and line of sight motion of prominence legs. Then I discuss about the short period oscillation present in the prominence. Finally, I end with the conclusion. Then what is the solar prominence? Solar prominence is observed at a solar atmosphere and it has loop-shaped magnetic structures embedded in the solar photosphere. It is staying against the gravity with the help of magnetic field present in the sun. The prominence is classified into two, quiescent and active region prominence according to presence of active region surrounding around it. The lifetime of prominence varies from few hours to couple of days, and temperature ranges from 4,000 Kelvin to 20,000 Kelvin. Motivation of my work. The solar prominence is small in size compared to the other features like solar flare and CMEs. The fine scale structure and inner dynamics of prominence are not yet fully understood. The combined observation of motion in plane of sky and a line of sight direction is very rare. Some of the prominence exhibit rotation, and according to previous studies, it is due to photospheric vortices under the prominence and associated flares in and UV waves. But its driving mechanism is to be further studied. Prominence has low temperature compared to surrounding corona and chromosphere, and it makes the temperature estimation important. Different types of oscillations are observed inside the prominence. It may be due to propagation of MHD waves present in the prominence. So it may help us to explain the coronal heating problem. The prominence is observed by two space-based observatories, Interface Region Imaging Spectroscopy, IRIS, and Atmospheric Imaging Assembly, AIA, onboard Solar Dynamic Observatory. The figure shows the AIA image of at a 171 angstrom, and the white box illustrates the IRIS field of view. The IRIS data has three spectral range of observation, two in far ultraviolet region from carbon and silicon, and one in near ultraviolet region from magnesium H and K line. IRIS data contains litho images also. AA observed the prominence at a 171 angstrom, 193 angstrom, 211 angstrom, 304 angstrom also. In data analysis, we used the time slice method and a local correlation tracking to study the plane of sky motion of the prominence. The Doppler velocity estimated from magnesium and silicon lines are used to study the line of sight motion of the prominence. The short period oscillation present in the prominence is studied with the help of wavelet analysis. The figure shows the dynamics of the solar prominence from 1231 to 1335 UT. The prominence rotate about the axis in figure C. We can see here a black line. The period of rotation is found by time slice method. The intensity variation along the white line in this figure with respect to time is shown in figure A. The intensity variation at a white mark is shown in figure B. The time difference between two peaks correspond to 180-degree rotation and a period of rotation equal to 1.02 hours. It makes a speed of 11.2 km between two legs, calculated by multiplying the separation between two legs and the angular velocity. In figure A, the north part of the leg is marked as 1 and the south part of the leg is marked as 2. The motion of two legs are tracked by minimum search method shown in the bottom figures. These two figures. It is clear that the north leg only exhibits the oscillation along the plane of sky, but it is not possible to identify the motion is due to rotation or transverse oscillation in plane of sky. The line of sight velocity must be studied to confirm it. The plane of sky motion of legs also studied with the local correlation tracking by AIA images at a 193 angstrom with a time interval of 4 minutes. The green arrows in the figure shows the direction of velocity vectors and the direction of velocity at the two different times, 1243 and 1323 UT. The direction of velocity is changed from clockwise to anti-clockwise after half an hour. The time evolution of velocity vectors is shown in the video. Here the time starts from 1231 and here this green arrow shows the velocity vectors and it is pointing to northward at the initial time, and after half an hour it is changing to opposite direction. That we can see in the result from the LCT analysis. The Doppler velocity of the prominence is studied from iris spectral data of magnesium HNK lines and a silicon. The figure shows the Doppler velocity at a 6 different time of observation, and a blue color represents the movement towards the observer, and a red color represents the movement away from the observer. The Doppler velocity variation along the white line drawn in the time-slice method we have across the prominence legs for 3 wavelengths, magnesium K 2796 angstrom and a magnesium H 28803 angstrom and silicon 1394 angstrom at a 1243 UT is shown here. These three figures. The Doppler velocity increases from south to north, indicates the clockwise rotation, and the Doppler velocity variation across the prominence legs is about 11 km per second. It validates the time-slice method and a LCD result. Here, these figures shows the Doppler velocity variation at a two different time along the white line we shown earlier. The Doppler velocity decreases from south to north after half an hour. In these figures, the Doppler velocity decreases from this indicates the anti-clockwise rotation, so we can conclude that the prominence legs exhibit torsional motion instead of rotation. The torsional motion of this prominence is studied by three methods: the time period and a 11.2 km per second velocity variation is calculated from time-slice method, local correlation tracking, and Doppler velocity. And this time period and 11.2 km we can calculate from the time-slice method. The LCT result shows the change in direction of velocity vectors after half an hour, and it is also present in the Doppler velocity, confirms the it is a torsional motion. The short period oscillation present in the prominence is studied by fast Fourier transform and wavelet analysis. The power in the frequency range 0.5 MHz to 6.5 MHz is shown here. Left one is the FFT from intensity data of magnesium, and the right is the FFT from silicon. A large power is observed between 0.5 to 2.5 MHz. The power in the range 0.5 to 1.5 is due to rotational motion of the prominence. The frequency range 1.5 to 2.5 MHz is equal to 7 to 11 minutes. The wavelet analysis of intensity data at these bright regions in the power spectrum gives a clear picture. These two figures are the result of the wavelet analysis of intensity versus time from iris in magnesium 2796 angstrom and a silicon 1400 angstrom. Here it is clear that a change that a large power is present in the range of 7 to 11 minutes in 3 wavelength regions, including at a 193 angstrom from AAA also. It proves the presence of oscillation in wall prominence, and it can be related to alpha waves propagating along the magnetic flux tubes. Conclusion of my work. The plasma motion of the prominence is studied with both imaging and spectroscopic data from 2 observatories. The prominence is rotating with a period of 1 hour from time-slice analysis of STO bar AA 193 angstrom, and the rotation makes a velocity gradient of 11.2 km per second between 2 ends. The Doppler velocity variation along the line used for time-slice analysis is about 11 km per second, indicates the clockwise rotation and matches with the calculated velocity gradient from time-slice method. A change in plasma flow is observed after half an hour from LCT, support the Doppler velocity results. That is, prominence exhibits a torsional motion instead of rotation. The prominence oscillation is detected between 7 to 11 minutes from a wavelet analysis of SDO bar AA 193 angstrom, iris in magnesium 2796 angstrom, and iris in silicon for 1400 angstrom also. Thank you for your attention.
Thanks for the nice overview of the analysis of your event. It's time for questions. We have a good amount of time for questions. So please go ahead and raise your hands.
Questions. Rakesh, go ahead and ask your questions.
Yeah. Hi, Jacob. Nice talk and nice work. So I have 2 questions. So first of all, what is your interpretation of this torsional motion?
Actually, from time-slice method, we have found that this north part of the leg is only rotating.
Yeah, that's fine.
Here we can see that the LCT also showing it is rotating in one direction in the initial stages, then after it is in the opposite direction. That is also clear from Doppler velocity, because to confirm a rotation we require plane of sky motion and a line of sight direction.
No, I believe it is torsional motion, but I am asking about the physical interpretation. How do you interpret it?
Okay, in previous literatures, we can have the interpretation like photospheric vortices and maybe associated flares also.
Okay. And my second question is does this torsional loss periodicity match with this torsional wave and MHD wave periods? Have you checked with that?
I didn't check.
Okay, maybe you can check with that. And also my third and last question is when you are playing the movies of LCT, so could be because of the above arrows, but I don't know, but I don't see much of the rotation in the from the eyes. So could be obstructed by these green arrows, but I'm not sure. But from the movies, I could not see much of the rotating filament feature.
Mostly this leg part is actually rotating.
Yeah, could not see it. Maybe when was that event? I mean, the date or time?
I think it is 15th December.
No, like the year?
2017.
2007. Maybe I'll check with the JLUWare. Okay, thank you. Nice work.
Okay.
I see a hand raised by Ji Hao Yang. You can unmute yourself and please go ahead for asking questions.
Thank you for this talk. I saw that you showed the observation from iris that shows this kind of rotation, and then you interpret it as the torsional motion instead of the rotation. Actually, we also have a paper published on APJ in 2018, and we also use iris observations to do the similar analysis, and we found that this prominence loops, prominence folds, they are rotating, but it's kind of like a helical motion. I wonder, in your interpretation, this torsional motion are the prominence foot doing this kind of torsional motion in a whole part, or just some surface materials are doing this torsional motion?
In the from area 193 angstrom, we used it to study this plane of sky direction. So this is absorption spectrum, maybe inner core it may be showing.
Okay, so so what I mean is that we can see a lot of materials from the prominence field. Are these materials doing this kind of torsional motion just for the surface materials, or the whole field are doing this torsional motion?
It may be some flux emergence from the inner photospheric also. Like if we observe the magnesium, it may be surrounding prominence, but with 193 angstrom, it will be in inner core observation, it will be.
Okay, thank you.
Okay, let me check if there are any questions here. Any questions? No. Okay, Arun, we can move on to the next talk.
Yeah, I think we can move on to the next talk, and everybody who wants to ask question and has not get time, they can ask on the chat box or also in the Slack channel. So we move on to the next speaker, Abhishek Srivastava from ITBHU. He will be speaking about the instabilities in the chromosphere.
Yeah. So is it visible now?
Yes, yes, it is.
Okay. So good morning, everybody. I'm Abhishek Srivastava from IIT BHU Varanasi. And today I'll be talking about instabilities in the solar atmosphere. Some emphasis would be given to chromosphere also. So I would start with this very general slide, that the general notion of instability is that the growing perturbations may lead instabilities on contrary to the wave motion. So if any system in general would be under the consideration of certain forces, so either it would lead the stable oscillations when omega would have real solutions, or the instability would grow when omega would have a pure imaginary solutions. So stability and related oscillations or instability, they may be the two faces of the same coin of the same perturbations. So I would come to this point that physical nature of the perturbations and systems configuration decide the mode of evolved instability. So with this general description, I would move and I would try to find out the discussion of first magnetic instability, and that is kink instability. This is the instability which is observed in a variety of magnetic structures in the corona as well as in the chromospheric structures too. So here I would take a very unique example, and that example is a highly twisted coronal loop, which was observed by Trace long back in 2007. And the most interesting stuff is here. So once we see the SOT observations of the similar loop, so its chromospheric counterpart also leads the display that there are a variety of internal threads are there, and they are visible there, and they are twisted, and they are showing some dynamics. So the twist is present in a predominant manner over this flux tube, and you can easily count the twist in this image there. This is the high resolution image. So the physics is there. If we consider the half part of the tube as a straight twisted tube, the pitch, which is an important parameter, could be related to the length, half length of the tube, and number of twists as follows. That is 2 pi p equals to L upon n twist, where p is a kind of significant parameter, which is the multiplication of the radius of the tube to the ratio of longitudinal to azimuthal feet. So the total twist angle is then phi equal to 2 pi n twist, that would be L, which is the half length of the tube, B phi over A BZ. So using these high resolution observations of the twisted tube, we could measure 2 pi p, that was approximately equal to 10 megameter, and that could lead us for the estimation of phi, and that phi was 6 pi, which was crossing the Kruskal-Safronov instability criteria of the straight tube, and that was phi greater than 2 pi. So what this is doing, this is trying to make M equals to kink mode perturbations growing in the form of kink instability. So these kind of twist evolution is very important for making the tubes going towards the kink instability. Torok has showed that curved loop with major to minor radius ratio 5 is subjected to the kink instability with a twist which is almost equal to the critical twist of 3.5 pi. So these kind of twists, when they are crossing certain threshold value, they are leading towards the kink instability, which is one of the very important magnetic instability. When we talk about another class of instability, that is sausage instability, so there is not an observational evidence there in the solar structure, and there is only one report which is done by us several years ago, and we got the evidence of sausage instability in the eruptive prominence, cool prominence, just before its eruption. So this was the observational description of sausage instability. I would explain it a bit later. So the physics is that when we consider the morphological parameter of this observed prominence, and the length 2L was 72 megameter and radius was approximately 1 megameter. So we could use the limiting condition for the kink instability, which was 2L greater than lambda s, where lambda s is the kink perturbation wavelength. And that was under limiting condition equal to 2 pi a bz by b theta. So by this equation and observed parameter, when we measured the mod of b theta over bz, which was roughly equal to 0.08 for the kink instability, that was shorter than the same for the sausage pinch instability, and that was greater than 1.4. So we concluded that this prominence was subjected to the kink instability first. So you can see here that a kinking was inherent there in the tube initially, and their internal reconnection would lead then the formation of bulges as well as the pinch region there over the tube. And with the time, this is smoothed out then thereafter. So we claim that this is the first observation of sausage instability that arose in the prominence there, which was observed on 12 September 2011. So the classical physics lie in the two scenario. There could be a Z pinch situation or theta pinch situation that may be there. So in the first situation, the axial current would jointly work with the azimuthal component of the magnetic field of the tube, and that could lead the Lorentz force, which may try to pinch the region in between over the tube. And the next region, which would be here, that would form the bulges, where the concavity of the surface of the tube would lead the decrease in the ambient field there, and that will cause the growth of the sausage perturbations there. That was the longitudinal perturbation within the tube. So bulges are formed, as well as pinch region or neck regions were formed there, which were the narrow region. And we observed the same conditions in the AIA observational baseline. So the other scenario could be theta pinch, but the effect would be same, where the axial ambient magnetic field would jointly work with the azimuthal current density of the tube, and the similar effect would be caused. So these two instabilities are the examples of the magnetic instabilities in the magnetic structures, and they could lead to the variety of eruptions there in the solar atmosphere when they do occur there. Apart from these magnetic instabilities, there are other interesting instabilities, and the famous one is the magnetized fluid interfaces and their instabilities. And the name is well known to all of us. One is Kelvin-Helmholtz instability. So Kelvin-Helmholtz instability occurs due to the velocity difference of two fluids at the interface. And for this schematic, the condition of KH instability could be that the velocity in first layer will be greater than the alpha velocity in the second layer. So this kind of situation, once it arose, in the fluid interface. So it could lead in the magnetized solar atmosphere and corona the dynamical events, and could lead the shearing motions under the KHI that can further cause turbulent motions and lead plasma dynamics. So here is the example where the eruptive flux slope was trying to go away and trying to erupt, and its flank is showing the evolution of KHI vortices. The another very fascinating one is the relative instability that arises at the interface of two fluids of different density. If the heavy fluid is supported by the lighter fluid and the interface is perturbed against the gravity, the following conditions holds good, which is G dot del rho less than 1. So the instability and related perturbations would grow at the surface. The presence of magnetic field, likewise in solar atmosphere, in the localized solar atmosphere, can cause the suppression of these kind of instabilities. So the presence of magnetic field would lead some kind of stability while these instabilities are growing there. So this is the typical cartoon for the RT instability, where at the interface, the characteristic perturbation wavelength is there, and it is causing the wavelength, it is causing the perturbations there, and that perturbation is growing non-linearly, and it is creating the plume-like structure. So this kind of instability is observed in the quiescent prominence plasma in the chromosphere. You can see here, this is the report by Ruteo et al. In 2010. And one can clearly see the case 1, where the plumes are developed. In case 2, the another set of plumes are developed. So the basic feature in the observational baseline is that self-similar plumes. And if they grow much higher and higher, so this is the non-linear regime of the RT instability. And the another important feature is that onset of these instabilities, they can try to suppress the regular oscillation. And it is a very obvious feature of the growth of the instability. This is another example, which is given by Tom Berger and colleagues. And you can see here, again, the prominence system. So in this prominence system, one can see that over the prominence cavity interface, there are the vertical structure, plume-like structures that are growing, and they are well grown, and suddenly a shear flow is started at the interface. And that shear flow is basically creating a kind of irregular oscillations at the interface. You can see by the red curve, and then it get regularized. So there's a oscillatory motions that is present now at the interface, and they interpreted these oscillatory evolutions in terms of coupled KH instability there. So in prominences, in such kind of chromospheric large scale structure, the RT and coupled KH instability is also seen there in such systems. Apart from large scale chromospheric structures, the KH unstable vortices are also observed in the chromospheric jet. You can see here, this is one recent observations from Swedish Solar Telescope, which is done by Dato Kurudje and colleagues in 16. And there is an observation of typical chromospheric jet, which is popping up in the atmosphere. And the top image is showing the top view of this jet. So initially at t equals to 0 second, this was showing a nice circular geometry. But as time is passing, which is 9.38 and so on seconds, so nodular structures are getting developed, and this is increasing and increasing in terms of nodular structures. So this is the typical feature of the evolution of KH unstable vortices in the chromospheric jet. And reason could be very obvious, because this chromosphere, the field lines, they are propelling the jets upward, and due to the shear motion in the Z body, these kind of KH instability and related vortices are evolving. I would take another example, which is recently done by my former PhD student, Sudhir Kumar Misra. He has recently completed his PhD. So he has observed the Rayleigh-Taylor instability as well as coupled KH instability by SDO AIA observations, but in the eruptive prominence. So you can see here, the eruptive prominence is there, and he identified two plume-like structures over the cavity C. So the top panel image is showing the time sequence of the evolution of plume P1, And similar, another plume is developing in the lower panel with time, and you can see that this is termed as P2. So what he has done, he has applied very basic concept of the RT instability. So these two plumes, when they are launched from the interface, which is prominence cavity and prominence interface, so the minimum separation was estimated, and that was the distance, minimum distance between the two plumes, and it was estimated as 41 megameter. So this is typical critical wavelength of the perturbations. And it is very
2 minutes.
Okay. And classically, you can find out the formula for the growth, and this is having gravity term as well as magnetic field term, and they are having opposite sign. So one can say that magnetic field related term is trying to stabilize the system. So Sudhir has done some initial diagnostics. For example, once you apply the most stable state using this equation, as well as some measured quantities like density in the plume and prominence interface like rho H and rho L. So you can estimate the magnetic field and its minimum value, which is 1.2 Gauss. And one can estimate the minimum value of olfactory velocity, which is 31 kilometer per second at the prominence interface. And by using these parameters, diagnosed parameters, as well as the estimated parameters by DM analysis, one can calculate the maximum theoretical growth rate that comes here 1.95 into 10 to the power minus 3 per second. So this growth rate was matching well with the observed growth rate, which is calculated by using this formula, which is given in Berger's paper and Rutova, and basically proposed by Rutova et al. So you can see the instability, such kind of instability, if they are well observed, so they can lead some kinds of diagnosis of the local plasma there, and they can be estimated precisely in terms of their growth rate, etc. So seared and rolled plasma structures emitted in the falling segment of the prominence is also observed, and this is after the stabilization of the plumes and related RT instability. So KH instability is also evolved in that particular region. So there are several efforts in terms of MSD models. So basically they deal with the interface instability, which is the classical scenario. So you can see some models like by Teradas and Hillier. And similarly, the interface models, due to the shear motion of the fluid interface, is leading to the KH instability, and it is well connected with the observations by Iris. So apart from these exotic instabilities, there are other instabilities. I would running out of the time, so I will just name it. Yeah. So there are thermal instabilities and some other instabilities which are listed there. They are very important physical processes in the chromosphere. This is general conclusion. Thank you very much. So in the era of high resolution observations, it's significant to understand the evolution of these instabilities and their properties in connection with the wave-like perturbations. Instabilities could be important in imparting the energy to localized polar spatial scales. Their non-linear phase is very important, and it could be understood with the detailed observations in modeling. And it could be an important science case for Aditya, Soot, and other observatories like Dictist and Iris. And modeling have a great avenue ahead, and one can do their modeling also with MSD codes or through our multi-fluid codes. Thank you very much.
Thank you, Abhishek, for this very nice talk. We have only time for only one quick question. Rakesh, do you have a question you want to ask?
Yeah. So, hi, Abhishek. This is Rakesh. Nice talk. Yeah, so I was just wondering regarding the nature of the instability, is it safe to claim just from the morphology that is this RTH or this type of instability?
Morphology is an important feature.
Yeah, that I agree, but just from that
to observe the instabilities, because they are the characteristic perturbations. They evolve in that form. For example, plume in RT and other instabilities. But of course, if you have seen there, so there is some diagnostics that would be made. For example, in work of Sudhir, and that is matching the theoretical calculation with the observations.
Okay.
So basically, those kind of diagnostics would be required to further
confirm
the water basins and their evolutions.
Yeah, maybe I'll look at the Sudhir work much more closely, then I'll be able to.
Yeah, sure.
Yeah, thank you. Okay, nice talk. Thank you.
Okay, maybe he has raised his hand.
Yeah.
Yes.
I can ask.
To me?
Yes.
Yeah. Okay. I just want to add. I just want to say that Avi has presented a very comprehensive introduction to these different types of instabilities in the MHD environment of the sun. I just want to add that there might be another type of MHD instability, which is called weak instability. And this kind of instability can lead to the development of vortex shading. And we recently observed this in the superrocket region above the flare loops. So some people may be interested in that.
Yeah, sure. So we will read that paper. Is it published? Or?
Yeah, it was published. Yeah, the first author is Tanmoy.
Okay, good. We can discuss.
Thank you.
Okay, thank you. Let's move on to the next talk by Shaheen on global P modes in the solar chromosphere at high resolution. Shaheen, you can start.
Yeah, hello. Hi. Thank you very much. Hello, everyone. So we had a very nice review on chromospheric dynamics earlier today, this morning by Gianna and other speakers of this session. What I'm going to talk about is about another chromospheric characteristic, which is the G mode, global P mode, sorry, oscillation, or the 3 minutes oscillation in the chromosphere, which became a basic fact at the turn of this century through a number of studies. Here, for example, as you can see the title, there have been many studies showing this oscillation from both observation and simulation. And since then, as both either global oscillation, which is the average over the entire field of view, or in a specific non-magnetic or magnetic structures. For the later part, I mean, I'm not going to talk about, I'm sure that David just later today will give a review on those. But the global oscillation and this characteristic periodicity, when we look at all these studies in the previous years, last decade, we can see that they're mostly from the either very large field of views or from wideband images. And in terms of simulation, they're mostly from hydrodynamic simulations, or the simulation contain very weak magnetic fields. Only recently from very high resolution observations from the Swedish 1 meter solar telescope, the recent signature of the lack of the 3 minute oscillations, particularly in the H-alpha line for intensities. We can see in particular in these two studies from Samantha et al. And Krishna Prasad et al. That they found this lack of 3 minute oscillations in their observations. So we looked at this a little bit in more detail, and we tried to understand what's going on at the high resolution. So we start with the ALMA observation. As Jan also mentioned this morning, ALMA has started to observe the sun since 2016 with two bands, so-called band 3, band 6, 3 and 1 millimeter, they're millimeter observations, and they supposedly sample mid to upper chromosphere. So what I'm showing here on this figure are power spectra of 10 different ALMA data sets. And if you look at it closely, and these are the average power spectra, the power spectra which is average over all power spectra of individual pixel within the field of view. And if you look at it closely, you see only two of the power spectra, these red ones, the dashed lines, show power enhancement around 3 to 5 millihertz, which is what expected from previous studies in the chromosphere. Whereas, to our surprise, we didn't find any power enhancement in any particular frequency for the other 8 data sets. If we just want to compare with the little bit lower height in the atmosphere for the exact same region, from AIA 1600 channel, we could indeed find this power enhancement in this frequency range in all the 10 data sets here. So, of course, this is in lower chromosphere, in around temperature minimum, much lower height, and the difference here is with ALMA, we're looking at the upper chromosphere. So if we also compare with a little bit higher up from AIA channel, again, here on the right-hand side, it's this time from the 304 channel, which is transition region, and we do not see any enhancements at all around this 3 to 5 millihertz band. So I'm just showing a little bit more examples, a few more examples on this from a couple of the data sets from ALMA. Here is one of the data sets that if you look at the right panel here on the corner, we do not see any power enhancement in the 3 to 5 millihertz again. This is one of those data sets that couldn't find any enhancement in this region. And if we look at the magnetic field, here is the magnetogram from HMI, from the photospheric magnetic field. And the inner square here shows the field of view of the ALMA, field of view of the observation. But we didn't want to only look at the field of view of observation, but we wanted to look at also the extended field of view, because again, as Gian also mentioned this morning, it's very important the magnetic field in the chromosphere are not rooted only in the field of view that you're observing, but it could be in the neighboring region. So in the immediate vicinity of this field of view, we can particularly see this very strong enhanced network, that many of these loops that's coming and covering the field of view of the observation could be rooted in those or in other neighboring magnetic field. Here on the right-hand side, in the bottom right, what I'm showing here is the magnetic topology in the upper chromosphere. The red shows more the horizontal field and the blue shows more vertical. And you can see here that the so-called magnetic canopy, this magnetic field, has covered pretty much the field of view of the observation. It could be one of the reasons that we do not see what's coming from underneath. The oscillation coming from underneath could be obscured by this magnetic canopy in the upper chromosphere. So another example here is also for one of those data sets that we could not find any 3 to 5 millihertz oscillation. In this data set, we have also very strong field within the field of view of the observation, and also in the immediate vicinity, here is the large region. And if you look at the magnetic topology, here we can see also that we have this more horizontal field, which have covered part of the field of view, but also we have this very strong field, more vertical, but very strong field within the field of view. It's another, actually, one of the other mechanisms that people have suggested, that also the strong field could suppress the power in the upper chromosphere. So both the canopy effect and the strong field seem to play a role. So I'm showing first some other example from the ALMA data that I showed them in the power spectra earlier. This is one of those examples that we do see the 3 to 5 millihertz power enhancement in the power spectra. And if you look at the magnetic field underneath in the photosphere, we see it's very quiet, not only the field of view, but also in the, immediate vicinity. And if you look at the magnetic topology in the chromosphere, we do have these loops indeed, but they're organized in much smaller loops. They're organized in much smaller scales, and they're not as dense as what we have these loops to be covering the entire field of view. So that's the difference that we observe in this data set. So also another example I can show for this is this one, just very quickly. Again, we have the enhancement, and again, we have a very quiet area. If you look at those line of sight magnetic field range here, they're order of 100 Gauss. It's very, very quiet extended region. And again, we have a smaller loops here, a smaller organization, and we clearly see this the presence of the 3 to 5 millihertz. So this was the first study that we did. It's just been published. You can check, you're welcome to check the paper for more detailed discussions. But what we have done now, we have started to look at also other observation and simulation to better understand what processes are involved here. So I've showed a couple of examples. One example from the Swedish Solar Telescope, high resolution, high spatial resolution also. So here is a much larger field of view that SST could observe. You can see it's very quiet. It's a very quiet region. SST has observed this very small region here. And if I zoom in, it's a very small region. It's a very quiet region. Also, we have this small magnetic bright point, but we don't have much activity here. And if I just plot the power spectra for different wavelength position, I'm showing only a couple of examples here. So the example here is for this line position. Here is the blue one is the H alpha line core, and the other one is these are the distances in milliangstrom from the line core of the H alpha in the blue wing. And you can see that we have all the power enhancement at the 3 to 5 millihertz in the H alpha line core. It's a little bit less even enhanced compared to the other one, which is still upper chromosphere. So still the effect of the canopy could play a role, but we can indeed see this enhancement. If I look at another diagnostic, here is the calcium 8542, and we can still see in this position that I've plotted here in the upper chromosphere, we can easily see this enhancement. If we look at the image here, I'm also cycling through these lines here that I'm showing here, this wavelength position. If we go higher up to the line core, towards the line core, here we can see this very small and organization of the fibrillar structure, which is thought to be the magnetic field lines, so to map the magnetic field lines. And you can see that it's pretty much similar to what we were discussing earlier with the alpha data. Now, if I show another example with the Swedish Solar Telescope at high resolution, but this time for a very active region. So this is a very active region. It's again much larger field of view to see the scene. So these are two large sunspots here, but we observed here with SSD in between the two sunspots. I mean, this is a small region, but we observed this at high resolution. We have small pores. We have this plug region all over the field of view. It's a very active area. If I again plot the power spectrum here for those the same equivalent position I showed earlier, there is absolutely no power enhancement here. So it's what we observe here. And if you look at the images here, when we go toward the line core especially, you can see all this very thick and long fibers and filaments, which are covering the entire field of view, in addition to the strong field that we have at some other locations. So if I also show now for the H542, as I showed also for the quiet zone, still we don't see any power enhancement, and still we do see this all this fibrillary structure covering the field of view. So unfortunately, as John mentioned, also magnetic field measurement is a little bit more difficult in the chromosphere, particularly in the quiet zone, but we're still looking at different parameters from observation. But to better understand what we have observed here, we start also to look at some simulation, magnetohydrodynamic simulations. So we used Bifrost, which is a simulation, radiation emission simulation of the entire atmosphere. I'm not going to much talk about this simulation in detail. I'm sure Matt Sparson will talk about it later on Thursday about this. So here is a quiet zone simulation. Here is the magnetogram at the photosphere, base of photosphere I'm showing again. And here is what, if I plot them in the power spectrum again, for the two bands, I mean, here is for the synthetic millimeter bands, for those that I showed earlier for ALMA. We're doing it for other diagnostic also. But at the upper chromosphere, if we just plot the power spectrum, we clearly see in the quiet zone this power enhancement. By the way, here you can see all this swirl motion in the quiet zone, and this smaller organization of the magnetic field could be seen perhaps here in intensity, but also I could show the magnetic field topology. And here we can see also the swirl motion in line of sight, and you can see many of those are blue, which means that they're mostly vertical. Here in the quiet zone, we have also some reddish here, which is the smaller organization of the magnetic canopy all over the field of view. If we'll look at it from this side, perhaps we can better see those organization. Here is much higher up, and the top of the tube is much higher up, more into the transition region corona. But here in lower, a little bit lower, we can see this red lines here showing this more horizontal field in a smaller organization, and we have many of those vertical fields in between. So this is a magnetic field which seems to be playing a very important role. And if I show also you very quickly another example from Bifrost, this time from a more active region. This time is we have this very strong enhanced network, opposite polarity in the photosphere. And if I do again the power spectrum for the entire field of view for the synthetic millimeter lines, we do not see any power enhancement. We see a little bit for the band 6, which is formed supposedly a little bit lower in height compared to band 3. But also in the simulation, we have a more quiet region towards the corner. We have more activity, and those loops here you can see between this enhanced network more in the center. If I would just limit myself to this area, to this more active region area, then absolutely we don't see any power enhancement again. So that definitely plays a very important role. I mean, in the presence or lack of this 3 to 5 minute periodicity here, the oscillations here. If I just show here the magnetic topology, here is also, we can clearly see there's all these very long loops that is connecting with these two magnetic region here, these two opposite polarity enhanced network. And so they have basically covered like an umbrella. If you look at it from the side, again, perhaps it's clearer that we can see this canopy. I mean, I'm particularly here, I'm plotting only the lines reaching to the higher heights. I mean, it's the upper chromosphere and higher, and we can see this canopy like an umbrella, basically obscuring what we're coming from underneath. If I would plot them in all the lines, also from the smaller scale, of course, we do have this multi-layered canopy on top of each other from the lower photosphere to the upper chromosphere and higher up. And but this, if I only plot the line, I mean, the upper chromosphere, we can more clearly see the effect of this canopy.
Shaheen, 2 minutes.
Yeah, I'm just almost done. Yeah, just long story short, I mean, I tried to show you a couple of examples from both observation, different resolution, and also the simulation. But all of those, I mean, have share one common thing, and that's the small field of view, relatively a small field of view, which was not much studied for this global oscillation in past. So it brings me to the summary of what we have observed. In principle, the presence or absence of a 3-minute oscillation in the chromosphere we find is significantly dependent on the amount of magnetic field flux within the field of view and also in the immediate vicinity of the field of view, or the topology of the magnetic field at the chromospheric heights. So it can be through different processes, like the umbrella effect, so-called umbrella effect, that can obscure the whatever coming from underneath. So the other one could be power suppression, or so-called also is known as magnetic shadows, that at the presence of a strong magnetic field or the inclined magnetic field, the power can be suppressed. And also it could actually also be due to the significant variation of the height formation. Again, as Gian also mentioned this morning, that this temporal modulation of the height in the upper chromosphere can easily destroy the oscillatory signal. So that's also something that we should consider at the presence of the magnetic field. It becomes perhaps larger. The exact processes, physical process, which one plays a more important role is the cylinder investigation. But what's important again here is the magnetic field topology and flux plays a very important role. And that's the key to answer this question. Thank you very much.
Thank you very much, Shaheen, for this very nice presentation. There are several questions. First one is by Rajaguru.
Hi, Shaheen, this is Rajaguru. It's a very good presentation, excellent talk. If I understood correctly, is it a fair statement to say, based on your presentation, that if the magnetic fields are canopy-like, there are closed structures, horizontal field, you see a lot of suppression and you don't see the 3 to 5 millihertz oscillations. On the other hand, even if it is quiet, if it is vertical field lines, you see the lot of oscillations going up. Is that a fair statement?
This is something that we have seen, we have observed so far. Yes, I mean this more canopy effect. I mean, also what I said also is not the only thing. It's the canopy. Also, if we have vertical field, but we have a very strong field, it seems, I mean, the strong magnetic field also can suppress the power at this frequency range. This is something that has been shown, I mean, in many studies in past. I mean, so as I said, I mean, so it's known as the magnetic shadows. So both actually seems to play a role. But if it's quiet, if we don't have much magnetic field, magnetic flux within the field of view, and if we don't have this horizontal field like in playing as umbrella effect, then we do see those 3-minute oscillations. Yes, that's what we have observed so far.
Okay, thank you.
Okay, next question is by Yannick Auzi. Unmute yourself.
Oh, yes, thank you. Nice talk. I had, maybe you just answered it a little bit. You have the possibility to do the same analysis in a spatially resolved way, right? You don't need to integrate all your signal. Because I would be actually surprised if you didn't see any signature of the 5 minutes, for example, near the network points.
Yes, no. It's again, yes, of course. I mean, I didn't show it. If you check, for instance, I mean, the paper also from Alma, we have actually showed also this distribution of the power. I mean, it's the spatial distribution of the power. Indeed, we do have all different frequencies. We have even very high frequencies. Even from the same data set Alma, actually, we have had PhD students here have been looking at very high frequency waves. I mean, we have different even MHD waves within the field of view. But what I'm talking about here is the average oscillation, average power spectrum, because this is also something has been addressed, I mean, for many years, and which is very important. I mean, what is the dominating frequency in a very large field of view? But otherwise, indeed, we do have, I mean, the different frequency, as you say, I mean, around the magnetic network, I mean, we have 5-minute oscillations, and we do have even, as I said, even higher frequency, like even 20 millihertz or so. I mean, we have for the small magnetic elements.
Well, I sort of have a problem with that because, you know, the older works about the global modes or whatever you want to call them, they were obtained with a very poor spatial resolution and a little understanding of these magnetic canopy effects and so on and so forth. So I don't actually think that it makes much sense to compare.
I'm not comparing, and I didn't say, I mean, whatever I mean has found, I mean, so far is completely correct. I mean, but I don't think even it's only the spatial resolution. But the size of the field of view seems to play actually an important role, because when you average, over a much larger field of view, you basically have more quiet region, because you have more quiet area, and therefore it dominates actually the average, and you can see the peak here. So it's why it became a fact. And it was very surprising. First, to some of those people that actually have been studying this 3-minute oscillation, that we couldn't see in a small field of view any 3-minute oscillation, because it's a 3-minute, it's a small field of view, and it's only quiet sun or active region. As I say, if you do it, otherwise, the spatial resolution, I don't think plays a very important role here when you average over the entire field of view, but the size of the field of view plays a more important role.
Okay, thank you.
Okay, next question by Dipankar.
Yeah, hi Sahin. Nice talk. So I was wondering how precise is the formation heights of the different ALMA channels, what we have now. Why I'm asking this question is, are we in a position to say really this canopy height in quiet sun, real quiet, enhanced network region or active region, we may have at different canopy heights?
Yeah, that's a difficult question. We don't have a very certain. It's also Diana also mentioned this morning. We don't know exactly. We don't know the exact formation height. It's been predicted through some simulation prior to the ALMA observation that they are supposedly in the upper chromosphere, band 3, band 6 is even low chromosphere, mid chromosphere. But we have some indication that it seems these bands have contribution from different heights. There have been some, Sven Wedemeyer has a paper showing that even some contribution perhaps from the transition region and lower corona. Not much, but a little bit contribution. But so we don't know exactly. There are some studies based on the theoretical models. Juan has done this, has this paper, but it's not so clear yet. Where they exactly form. It's what's very clear. They have a very wide range of contribution in height. But what we see is why actually we have started to look at also for this particular study, we are starting to look at also SSC observation. We have narrowband observation. We know actually very exactly what we're looking at, and also from the simulation. And we found a consistent result in a way. It seems, the main contribution comes indeed from the upper chromosphere, mid to upper chromosphere, but they can have contribution from other heights as well.
It was really nice to see that you already see quite a bit of difference between a quiet sun, which is really quiet, and even if you have a say, enhanced network in the neighborhood, that really influences your result quite a bit.
Yes, because again, this is the chromosphere, and and we have this horizontal line. Just coming inside the field of view, right? They're rooted, outside, but they just cover actually the field of view if they are located nearby. So that's the thing. So it's very important actually in chromosphere to not look only at the counterpart, the field of view in the photosphere, because it can be completely different topology.
Yeah, thank you.
Okay, one last question by Tanmay, I think. He raised a hand first. Tanmay, you can go on.
Very nice talk. I have a little bit different question. So in the chromosphere in the lower height, we see this the oscillation are dominated by 3 minutes. But when you look at the corona is the presence of ubiquitous transverse wave with around 4 millihertz frequency are present, right? Which is seen by COMB or AIA. So do you think there is this some kind of wave mode conversion can cause the generation of this transverse wave in the canopy?
Yeah, it can be. There are many different studies actually have discussed this frequency differences and similarities through the entire atmosphere. One I can remember now, it's like Richard Morton has this very nice study from the photosphere to corona. Let's compare this power spectra. You can see some of the higher frequency and actually disappear before reaching to the corona. The speculation there was that they could be dissipated in chromospheric height, but of course, we have this mode conversion that can even occur multiple times at different this equipartition level. But what exactly happened, I think it's something that needs to be really inspected in more detail to see what's happening between the chromosphere and between the chromosphere and corona. So I cannot really comment exactly what could be, but indeed, mode conversion and some dissipation could play a role. Also, the waves, are not necessarily coming from underneath. Could change, and or could be even excited, in the region in corona.
Okay, since this is the last talk, we may take one last question. Let me not disappoint Krishna. Krishna, go ahead and ask your question.
Thanks, Nagaraj. So, hi, Shaheen. As Gianna pointed out, I'm really surprised as well that you did not find any bump in the power spectra. So I just wanted to make sure, like, if you look in the photosphere, since these are intensity oscillations, you have opacity changes and small amplitudes. That's one of the reasons. But in the chromosphere, since you have the full spectra, did you try to look at the velocity oscillations just to make sure that there are no opacity changes or something?
No, we have looked at it. I mean, I didn't show. I mean, we are actually doing this oscillation in the velocity, lines of velocity as well. Now, I mean, in lines of velocity, actually, in many of those, I mean, you can see actually indeed this 3-minute oscillation. It's not opacity effect only, but it could be the canopy. I mean, one of the at least speculation we have at the moment we're discussing. I mean, it could be the canopy oscillating, but that it doesn't show it in intensity images. But again, I mean, if you do average the spectra over the entire field of view, even if you're in your study, I'm sure that you don't see other peaks at other frequencies. But if you look at the distribution of the power, if you look at the power at individual pixels, you do have this power enhancement at other frequencies. Indeed, you do have it, I mean, even in higher frequencies. But if you average it out, I mean, and then it's basically, I mean, you see only the dominating power, the dominating frequency that you get. So it's very different than looking, I mean, only at the individual pixels. This is one important thing, and also it's very important that this so-called dominant power maps, I mean, are not the best way to look at the spatial distribution. I mean, it has to be interpreted at least with great caution, because even, I mean, in the one power spectra, you may have multiple very large peaks, I mean, with a very large power, which are comparable. But if you pick only the frequency corresponding to the largest power, I mean, it could be also dangerous a little bit. So you indeed have a very large range of spectra, power spectra in your field of view.
Just to make sure that you do the averaging in the power spectral domain, right? Not in the intensity domain.
No, in power spectral domain, yeah.
Okay, thanks.
Okay, thanks very much, Shaheen. And
thank you.
Come to the end of this session, and we would like to thank all the speakers and Arun.
I would like to add that there may be more questions definitely from the speakers of this session. So everybody in the audience can join the Slack channel and ask the questions there. And I also asked the presenters of this session to join the Slack channel so as they can respond to the questions asked directly to them. So thanks for the presentations in this session. We meet again at 2 o'clock Indian time. Till then, have a nice time.
Come back at 1:45, just 15 minutes before 2 o'clock.
Okay.
Yeah, at 1:45, we'll join back for the next session. So we have a lunch break here, and whatever time it is, you take a break for 1 hour, 15 minutes.